Hello there, and welcome to Physics with William, the place where we take complicated ideas about the universe and walk through them slowly, carefully, and without rushing past the details. Tonight, we're turning our attention to something so common that we almost never stop to question it. It's in your room right now, it's bouncing off the walls, reflecting from your screen, travelling from distant stars, and quietly carrying information across the universe at the fastest speed anything can travel. We're going to talk about the photon, not just what it does, not just how fast it moves, but what it actually is. What is a photon really made of? That question sounds simple at first. We're used to asking what things are made of. Tables are made of wood or metal, cells are made of molecules, molecules are made of atoms, atoms are made of protons, neutrons and electrons, and those, we're told, are made of quarks and other fundamental particles. So naturally we want to keep digging. If light is made of photons, then what are photons made of? Before we go further, let me ask you something small but grounding. Take a quick look around you. How bright is the room you're in? Is the light coming from a lamp, a screen, a window? Are you listening in the evening, with artificial light filling the space? Or is it daytime where you are, with sunlight doing most of the work? Wherever you happen to be, that light reaching your eyes is made of countless photons. They've travelled from their source, interacted with surfaces, and finally struck the photoreceptors in your retina. And all of that happens so routinely that it feels effortless. If you enjoy these slow explorations of physics, if you like unpacking questions that seem simple, but turn out to run deep, consider liking the video or subscribing. It helps this channel reach others who enjoy learning at this pace. Now let's move carefully into the question itself. When we ask what something is made of, we usually mean that it has internal structure. We expect smaller pieces inside. A car is assembled from components. A molecule has atoms inside it. Even a proton, which once seemed fundamental, turns out to be composed of quarks held together by gluons. So the instinct to ask what a photon is made of comes from a long history of discovering that nature often hides additional layers beneath what first appears simple. But photons are not like protons. They are not tiny solid beads with smaller pieces rattling around inside. To understand why, we have to begin by reminding ourselves what a photon is in the first place. A photon is the smallest possible unit of light. More precisely, it is the smallest discrete packet of electromagnetic radiation. When light travels through space, it does so in quantized units. Each of those units is a photon. That idea was not always obvious. For a long time, light was thought to be purely a wave, something like ripples moving across water. In the 19th century, James Clerk Maxwell showed that light could be described as oscillating electric and magnetic fields travelling through space. His equations were remarkably successful. They predicted the existence of electromagnetic waves and even calculated their speed, which matched the known speed of light. So by the late 1800s, physicists were confident that light was a wave. It could interfere with itself, diffract around obstacles, and produce patterns characteristic of wave behaviour. There seemed to be no need to think of light as particles. Then came experiments that didn't quite fit that picture. The most famous of these was the photoelectric effect. When light shines on certain metals, it can eject electrons from their surface. Classical wave theory predicted that increasing the intensity of light should increase the energy of the ejected electrons, but experiments showed something different. The energy of the electrons depended on the frequency of the light, not its intensity. Even a very dim ultraviolet light could knock out high-energy electrons, while a very bright red light could fail to eject any at all. In 1905, Albert Einstein proposed a bold explanation. Light, he suggested, does not only behave as a continuous wave, it also comes in discrete packets of energy. Each packet carries energy proportional to its frequency. These packets were later called photons. This idea explained the experimental results perfectly. It also introduced a fundamental shift in how we think about light. From that point forward, light had a dual character. It behaved like a wave in some experiments and like a particle in others. Over time, This duality was incorporated into quantum theory. The photon became one of the fundamental particles in the standard model of particle physics, and here is where we approach the core of our question. In the standard model, the photon is considered an elementary particle. That word has a specific meaning. An elementary particle is not made of anything smaller. It has no known internal structure. It is not composed of subcomponents that can be separated or rearranged. As far as our best experiments can determine, the photon is fundamental. This is not a casual claim. Physicists have spent decades smashing particles together at extremely high energies to probe their internal structure. When we collided protons at high speeds, we discovered quarks inside them. When we probed atomic nuclei, we found that they were made of smaller constituents. Each time we looked closer, new layers appeared. But when we examine photons, we find no evidence of internal pieces. There are no sub-photons hiding inside, no smaller building blocks that can be revealed by higher energy experiments. If photons had internal structure, we would expect to see deviations in scattering experiments or other measurable anomalies. So far, none have been observed. That leads to an uncomfortable but important conclusion. A photon is not made of anything else. It is not built from smaller parts. It is a fundamental excitation of the electromagnetic field. Now that phrase deserves attention. A fundamental excitation of a field. In modern quantum field theory, particles are not viewed as tiny solid objects in the traditional sense. Instead, the universe is described as being filled with fields. There is an electron field, a quark field, a Higgs field, and an electromagnetic field, among others. These fields exist everywhere in space. They are not confined to particular locations. Even in what we call empty space, these fields are present. A particle, in this framework, is a localized excitation of its corresponding field. Imagine the surface of a calm lake. The water is always there, even when it appears still. If you toss a stone into the lake, ripples spread outward. Those ripples are disturbances in the water. In a very rough analogy, a photon is like a ripple in the electromagnetic field. But unlike water ripples, which are made of water molecules, the electromagnetic field is not made of smaller material pieces. It is a fundamental entity in our theory. So the photon, as an excitation of that field, does not have constituent parts. It is the smallest possible disturbance that can carry electromagnetic energy. This idea shifts the way we ask the original question. Instead of asking what a photon is made of, we might ask whether the electromagnetic field itself is made of something deeper. And here, physics becomes more speculative. Some theories attempt to go beyond the standard model. String theory, for example, proposes that fundamental particles are tiny vibrating strings. In that picture, what we call a photon would correspond to a particular vibrational mode of the fundamental string. However, string theory remains unconfirmed. There is currently no experimental evidence that photons are made of strings or any other substructure. As far as all tested physics is concerned, the photon is elementary. It also has a set of unusual properties that distinguish it from many other particles. For one, it has no rest mass. That does not mean it has no energy. On the contrary, its energy is determined by its frequency. But unlike electrons or quarks, it does not have a mass when at rest. In fact, it cannot be at rest. A photon always travels at the speed of light in a vacuum. There is no reference frame in which it stands still. It also carries no electric charge. This is significant because charged particles can interact directly with electromagnetic fields. Photons, being the carriers of the electromagnetic interaction, do not carry charge themselves. They mediate forces between charged particles. When two electrons repel each other, that repulsion can be described in quantum electrodynamics as an exchange of virtual photons. These are not photons you could detect with a camera. They are temporary disturbances that appear in the mathematical description of interactions, but they reinforce the idea that photons are fundamental messengers of the electromagnetic force. So if a photon is not made of smaller particles, what gives it its properties? Why does it have energy proportional to frequency? Why does it move at a fixed speed? Why does it have spin equal to 1 unit of angular momentum? These properties are not the result of internal components interacting. They arise from the mathematical structure of the electromagnetic field and the symmetries of space-time. In other words, they are built into the fundamental framework of the theory. This is one of the places where physics stops offering mechanical explanations in terms of smaller parts and instead provides structural explanations. The photon behaves the way it does because the underlying equations governing fields and symmetries require it to. If that feels less intuitive than saying something is made of smaller pieces, that's understandable. Human intuition evolved in a world of solid objects and mechanical interactions. Quantum fields are not directly accessible to our senses, but experimentally this framework has been confirmed with extraordinary precision. Predictions of quantum electrodynamics, the theory describing photons and their interactions, match experiments to many decimal places. As we continue, it will be important to refine this picture further, because even though photons are considered elementary, that doesn't mean there's nothing more to understand about them. The fact that something is fundamental does not make it simple in every respect. Photons exhibit wave-particle duality. They can interfere with themselves. They can become entangled with other particles. They can be absorbed and emitted in discrete processes by atoms. So while the direct answer to what a photon is made of appears to be nothing smaller, the deeper story involves understanding how something can be both particle-like and wave-like at the same time, and how its properties emerge from the structure of quantum fields. To get there, we need to take a closer look at what we actually observe when we detect light, and how those observations guide our understanding of what a photon really is. When we ask what a photon is made of, it's tempting to start with theory, equations, fields, quantum models, but it's often more useful to begin somewhere simpler and more grounded. Before we talk about what light is at its deepest level, we should ask what we actually observe when we encounter it. What do we truly see when we see light? Right now, if your eyes are open, light is entering them. It may be coming from a lamp, from a window, or from the screen in front of you. But here's something that's easy to overlook. You're not directly seeing photons in flight. You're seeing the result of photons interacting with matter. In fact, under normal conditions, you never see a photon travelling through empty space. If a beam of light passes through a perfectly clean vacuum and nothing interrupts it, there would be nothing visible about its path. The beam becomes visible only when photons scatter off dust, mist, smoke, or some other particles suspended in the air. What you perceive as a glowing line in space is actually a series of tiny interactions between photons and matter. This is our first clue. Light becomes visible when it does something. When it reflects, scatters, or is absorbed and re-emitted. Seeing is not about photons drifting quietly across space. It is about photons interacting with atoms in your eyes. Let's narrow in on that process. At the back of your eye is the retina, a thin layer of tissue filled with specialized cells called photoreceptors. There are two main types, rods and cones. Rods are sensitive to low light levels. Cones are responsible for color vision and function best in brighter conditions. When photons enter your eye, they eventually strike these photoreceptor cells. Inside each photoreceptor is a molecule called retinal, which changes shape when it absorbs a photon. That shape change triggers a cascade of chemical reactions. Those reactions alter the electrical properties of the cell. Electrical signals are sent through neurons, travel along the optic nerve, and are processed by the brain. What you experience as brightness, colour, or shape is the result of that entire chain of events. At no point do you perceive a photon directly as a tiny object. What you perceive is the outcome of a quantum interaction between a photon and a molecule. So already, our question begins to shift. A photon is not something you can observe like a grain of sand. It does not appear as a miniature glowing bead suspended in space. It reveals itself only through its effects. This is not just a limitation of human vision. Even our most advanced detectors do not see photons in transit. Photodetectors work by absorbing photons. When a photon hits the detector, it transfers its energy to electrons in the material. That transfer produces a measurable signal. But once absorbed, the photon is gone. Its energy has been handed over. If we attempt to detect a single photon, we do so by setting up an experiment in which only one photon at a time reaches a sensitive detector. When the detector registers a signal, we infer that a photon arrived. But again, we're not observing a little object with shape and size. We're observing a discrete energy transfer. This leads to a subtle but important point. Our concept of a photon is built on patterns of interaction, not on visualizing internal structure. The photon is defined operationally by what it does. To understand why that matters, consider an experiment that has become central to quantum physics, the double-slit experiment. When light passes through two narrow slits and strikes a screen, it produces an interference pattern. Bright and dark bands appear, characteristic of wave behavior. This happens even if we send photons through the slits one at a time. If light were made only of classical particles like tiny bullets, we would expect each photon to pass through one slit or the other and produce a simple accumulation pattern behind the slits. Instead, over time, an interference pattern builds up. Each individual photon lands at a specific point on the screen, but collectively they produce a pattern that suggests wave-like interference. This is one of the clearest pieces of evidence that photons are not small solid objects with definite trajectories in the classical sense. When we attempt to measure which slit a photon passes through, the interference pattern disappears. The act of measurement changes the outcome. What does this tell us about what we are seeing? It tells us that photons do not behave like miniature billiard balls travelling along well-defined paths, nor do they behave like simple classical waves spread smoothly through space. Instead, they exhibit a type of behaviour that does not fit comfortably into everyday categories. When we detect a photon, we detect a localised event, a click in a detector, a flash in a photomultiplier tube, a chemical reaction in the retina. The energy arrives in a discrete unit. There is no such thing as half a photon being absorbed. Either the energy packet is transferred or it is not. But before detection, the description of the photon involves a probability distribution. The mathematics tells us the likelihood of detecting the photon at different positions. That probability behaves like a wave, spreading out, interfering with itself, and evolving over time according to the equations of quantum mechanics. So when we see light, what are we actually seeing? We are seeing the cumulative result of countless quantum events. Each event is a photon interacting with matter. Each interaction transfers a specific amount of energy. Our brains then assemble those events into a continuous visual experience. If you look at a bright surface, trillions of photons per second are striking your eyes. The brightness corresponds to the number of photons arriving per unit time. The colour corresponds to their frequency, which determines their energy. Red photons carry less energy than blue photons, but in both cases the detection happens one photon at a time. Interestingly, under extremely low light conditions, experiments have shown that the human eye can detect very small numbers of photons. In some cases, people can respond to flashes involving only a handful of photons. This suggests that the quantized nature of light is not just an abstract concept confined to laboratories, it is embedded in biological systems. Another important observation is that photons do not pile up inside a material in the way classical particles might accumulate. When a photon is absorbed, its energy is transferred to electrons in atoms or molecules. The photon ceases to exist as a photon. It is not stored as a tiny object. Its energy becomes part of the internal energy of the absorbing system. If the material later emits light, that emission involves the creation of new photons. These photons are not the same individual entities that were previously absorbed. They are new excitations of the electromagnetic field generated by changes in the energy states of electrons. This challenges another intuitive idea. In everyday language, we might say light bounces off a mirror. But at the microscopic level, reflection involves electromagnetic interactions between photons and electrons in the mirror's surface. The electrons respond to the incoming electromagnetic field and re-radiate energy. The outgoing light maintains coherence with the incoming light, producing what we perceive as reflection. Again, what we see is not a stream of tiny solid objects ricocheting off a surface. It is a series of quantum interactions governed by field equations. All of this reinforces a pattern. The photon is not encountered as a composite object. It is encountered as a quantized interaction. We infer its existence because energy arrives in discrete packets, consistent with a particular frequency. We observe interference patterns that require wave-like descriptions. We measure momentum transfer when light exerts pressure on surfaces. In fact, light pressure is another concrete clue. Photons carry momentum, even though they have no rest mass. When light strikes a surface, it can exert a force. This has been measured experimentally and is used in proposals for solar sails in space exploration. The momentum of a photon is related to its energy and frequency. But again, this momentum is not explained by internal moving parts. It arises from the structure of the electromagnetic field and relativistic constraints. So what we actually see when we see light is a sequence of energy exchanges between the electromagnetic field and charged particles. Those exchanges occur in discrete units. The pattern of these exchanges can exhibit wave-like interference. The energy and momentum transferred match precise mathematical relationships. At no point in these observations do we encounter evidence of smaller components inside a photon. There are no signs of substructure, no indications that a photon can be broken into parts with fractional energy or charge. When a photon is absorbed, it disappears as a photon. When it is emitted, it appears as a whole unit. This does not prove that photons are absolutely indivisible in every possible future theory. Science always leaves room for deeper layers. But within the framework of quantum electrodynamics, which has been tested to extraordinary precision, photons behave as elementary excitations. They do not display internal complexity in any measurable way. It is also worth noting that our sensory experience smooths over the discrete nature of photons. Under normal lighting, the arrival of photons is so frequent that the quantized events blend into a continuous experience. We perceive a steady glow, not individual clicks. But the underlying reality consists of separate interactions occurring at extremely small scales and high rates. As we continue to unpack what a photon is, it will help to keep this in mind. Our direct experience of light is indirect. We never observe photons in isolation. We observe their interactions. Those interactions reveal key properties: discrete energy, momentum, wave-like probability distributions, and the absence of detectable internal structure. The next step is to revisit the older wave picture of light in more detail, because understanding how electromagnetic waves arise from Maxwell's equations provides essential context. Only by examining how the classical description works can we see clearly why the quantum description became necessary, and how the photon emerges from the transition between those two frameworks. Before the word photon entered physics, before anyone imagined light as a discrete packet of energy, there was a remarkably successful story about waves. That story begins in the 19th century with attempts to understand electricity and magnetism, two phenomena that had been studied separately for decades. What emerged from that effort was a unified description that would change physics permanently. Electricity and magnetism were originally thought to be distinct forces. Static electricity could attract or repel small objects. Magnets could pull iron filings into organized patterns. But experiments gradually revealed connections. Moving electric charges produced magnetic effects. Changing magnetic fields could generate electric currents. These relationships were quantified piece by piece until James Clerk Maxwell assembled them into a coherent mathematical framework in the 1860s. Maxwell's equations describe how electric fields and magnetic fields behave and influence one another. There are 4 core equations, and while their mathematical form is compact, Their implications are enormous. They show that electric fields can be generated by charges and by changing magnetic fields. Magnetic fields can be generated by moving charges and by changing electric fields. The key insight comes from considering what happens in empty space. Suppose there are no charges present, no currents, just a region of vacuum. Maxwell's equations predict that if an electric field changes in time, it creates a magnetic field. If a magnetic field changes in time, it creates an electric field. These two processes can sustain one another. Imagine a small disturbance in the electric field. That disturbance generates a changing magnetic field. The changing magnetic field generates a changing electric field. The cycle continues, allowing the disturbance to propagate through space. The result is a self-sustaining electromagnetic wave. When Maxwell calculated the speed at which such waves would travel, he found something remarkable. The speed depended only on two measurable constants: the electric permittivity and magnetic permeability of free space. When he plugged in the known values, the predicted speed matched the measured speed of light. This was not a coincidence. It meant that light itself is an electromagnetic wave. That realization unified optics with electromagnetism. Light was no longer a separate phenomenon requiring its own special explanation. It was simply a particular frequency range of electromagnetic waves. Lower frequencies corresponded to radio waves. Higher frequencies included visible light, ultraviolet, X-rays, and gamma rays. The entire electromagnetic spectrum emerged as a single continuous family. In this framework, there was no need to talk about photons. Light was described as oscillating electric and magnetic fields travelling through space. These oscillations were continuous. Energy was spread smoothly throughout the wave. The wave picture explained many observed behaviours of light. Interference patterns could be understood as overlapping waves adding constructively or destructively. Diffraction around small openings made sense as wave spreading. Polarization could be described in terms of the orientation of the electric field oscillations. For decades, this wave description seemed complete. Experiments confirmed Maxwell's predictions with high precision. Radio waves were generated and detected, confirming that electromagnetic waves existed beyond visible light. Everything fit together cleanly. But there was an unresolved question. If electromagnetic waves are disturbances in fields, what exactly are those fields? Early physicists imagined a medium called the luminiferous ether, a substance filling space that could support wave propagation. Sound waves travel through air. Water waves travel through water. It seemed natural to assume that light waves required some medium as well. However, experiments designed to detect motion through the ether failed. The most famous was the Michelson-Morley experiment in 1887. If Earth were moving through an ether, the speed of light should vary depending on the direction of motion. But no such variation was observed. The speed of light appeared constant in all directions. This null result created a crisis for the ether hypothesis. Eventually, Einstein's theory of special relativity provided a new framework. The speed of light was not determined by motion relative to a medium. It was a fundamental constant of nature, the same for all observers regardless of their relative motion. With relativity, the need for an ether disappeared. Electromagnetic waves did not require a material medium. They were oscillations of the electromagnetic field itself, which exists as a fundamental entity in space. Up to this point, the story still involved continuous waves. Energy in an electromagnetic wave was thought to be divisible indefinitely. A wave with half the amplitude would carry less energy, and so on smoothly. But as mentioned earlier, certain experiments began to challenge that picture. One of the most significant involved black-body radiation. When objects are heated, they emit electromagnetic radiation. Classical wave theory predicted that at high frequencies, the energy emitted should become infinite, a result known as the ultraviolet catastrophe. Experiments did not support this prediction. Max Planck resolved the discrepancy in 1900 by proposing that energy exchange between matter and radiation occurs in discrete units. He introduced a constant, now called Planck's constant, which set the scale for these energy quanta. Planck initially treated this quantization as a mathematical trick, not necessarily as a statement about the fundamental nature of light. Einstein took the idea further. He suggested that light itself is quantized. The energy of a light beam is not just divided during emission or absorption. The beam consists of individual quanta from the start. This created tension. On one hand, Maxwell's equations described light as a wave. On the other, experiments showed that energy arrived in discrete packets. The resolution came with the development of quantum field theory in the 20th century. Instead of choosing between waves and particles, physicists reinterpreted the electromagnetic field itself as a quantum object. In classical physics, a field assigns a value to every point in space and time. For example, the electric field at a point has a certain magnitude and direction. In quantum field theory, fields are promoted to operators. They can exhibit quantized excitations. These excitations are what we call particles. In this framework, the electromagnetic field is always present. When it is in its lowest energy state, we call that the vacuum. When it is excited in a particular way, a photon appears. This does not mean that the classical wave description was wrong. It means that it was incomplete. At large scales and high intensities, the quantum description reduces to the classical wave picture. A beam of light containing enormous numbers of photons behaves like a continuous electromagnetic wave. The oscillations of the field average out to the smooth patterns described by Maxwell's equations, but at low intensities or in situations involving individual interactions, the quantized nature becomes evident. Photons cannot be divided into smaller fractions during absorption. The energy exchange occurs in whole units determined by frequency. It is important to recognize that the electromagnetic wave and the photon are not separate entities in competition. They are two aspects of the same underlying quantum field. The wave description arises from the field structure. The particle description arises from the field's quantization. To make this more concrete, consider a simple example: a radio transmitter. When it emits a signal, it generates oscillating electric currents in an antenna. These currents create oscillating electric and magnetic fields that propagate outward as electromagnetic waves. At a large distance, a receiving antenna detects the incoming wave and converts it back into electrical signals. In a classical description, this is entirely continuous. But in a quantum description, the emitted radiation consists of vast numbers of photons corresponding to the frequency of the signal. Each photon carries a tiny amount of energy. The classical wave emerges from the collective behavior of many photons. Another example is sunlight. The sun emits radiation across a broad spectrum. At Earth's distance, the sunlight arriving per square meter per second corresponds to an enormous number of photons. The intensity feels continuous, yet at a microscopic level, the energy arrives in discrete quanta. All of this brings us back to our central question. If light can be described as a wave of electric and magnetic fields, and if photons are quantized excitations of that field, then asking what a photon is made of may be similar to asking what a ripple is made of. A ripple on water is not made of smaller ripples. It is a pattern of motion in the water. The water itself is made of molecules, but the ripple is an emergent disturbance. In quantum field theory, the electromagnetic field is not made of smaller mechanical components in the way water is made of molecules. It is fundamental in the current model. The photon, as a disturbance of that field, is not composed of smaller pieces. It is the smallest possible excitation consistent with the field's quantization. There is also a structural constraint that shapes the photon's properties. Maxwell's equations are invariant under certain symmetry transformations, including gauge transformations. This gauge symmetry is deeply connected to the existence of the photon. In fact, in quantum electrodynamics, the photon emerges as the force carrier required by local gauge invariance of the theory describing charged particles. That may sound abstract, but it carries practical implications. The masslessness of the photon, for example, is tied to gauge symmetry. If the photon had mass, the equations would look different. Experiments place extremely tight limits on any possible photon mass, and so far all evidence supports that it is exactly zero. The wave story also explains why photons have two polarization states. In free space, electromagnetic waves are transverse. The electric and magnetic fields oscillate perpendicular to the direction of travel. In quantum terms, this corresponds to the photon having two possible polarization states, related to its spin. So the electromagnetic story provides a foundation. It tells us that light is not a material substance moving through space. It is a dynamic pattern in a fundamental field. When that field is treated quantum mechanically, the smallest units of excitation are photons. This perspective shifts the meaning of composition. A photon is not made of smaller building blocks in the way atoms are made of protons and electrons. It is a fundamental unit of excitation. Its properties are determined not by internal components, but by the symmetries and structure of the underlying field and space-time. Understanding this wave foundation prepares us for the next layer of inquiry. Because once we accept that photons are quantized excitations of a field, new questions arise about how they behave when interacting with matter at very small scales, and why they sometimes act in ways that seem inconsistent with either classical particles or classical waves. For much of the 19th century, the electromagnetic wave description of light appeared complete. Maxwell's equations worked. Experiments confirmed them. Interference, diffraction, polarization, all of it fit within a clean mathematical framework. Light was a wave in the electromagnetic field, and that seemed to settle the matter. But physics has a pattern. Whenever a theory appears finished, experiments begin to probe its limits. Toward the end of the 1800s, several results began to surface that did not align comfortably with the classical wave picture. These were not vague inconsistencies. They were precise, repeatable measurements that resisted explanation. One of the earliest warning signs came from the study of thermal radiation. When objects are heated, they emit electromagnetic radiation. The spectrum of this radiation depends on temperature. Physicists attempted to calculate the distribution of energy across different frequencies using classical wave theory. The result, derived from known principles of electromagnetism and statistical mechanics, predicted that the energy emitted at high frequencies would increase without bound. In other words, a hot object should radiate infinite energy in the ultraviolet region. This prediction became known as the ultraviolet catastrophe. Experimentally, no such divergence occurred. Real objects emitted radiation with a peak at a certain frequency that shifted with temperature, and the energy at high frequencies dropped off instead of diverging. The classical calculation was clearly wrong. In 1900, Max Planck proposed a solution. He suggested that the energy exchange between matter and electromagnetic radiation could not vary continuously. Instead, it occurred in discrete units proportional to frequency. The energy of each unit was given by the formula E equals h nu, where h is Planck's constant and nu is the frequency. Planck did not initially claim that light itself was made of discrete packets. He treated quantization as a property of how matter absorbed and emitted energy. But the formula worked. It matched experimental data exactly. The ultraviolet catastrophe disappeared. Even so, the wave picture of light remained dominant. Many physicists considered Planck's quantization to be a mathematical trick, not a statement about the fundamental nature of radiation. Then came the photoelectric effect. When light shines on a metal surface, electrons can be ejected. Classical wave theory predicted three things about this process. First, increasing the intensity of light should increase the energy of the ejected electrons. Second, there should be a measurable delay between shining light on the surface and electrons being emitted because energy would accumulate gradually. Third, light of any frequency should eventually eject electrons if the intensity is high enough. Experiments contradicted all three predictions. Instead, scientists observed that the energy of the ejected electrons depended only on the frequency of the light, not its intensity. Increasing the intensity increased the number of electrons emitted, but not their individual energies. Moreover, there was no measurable delay. Electrons were emitted almost instantaneously, even at low intensities, and below a certain threshold frequency, no electrons were emitted at all, regardless of intensity. These results were incompatible with a purely continuous wave model. In 1905, Albert Einstein offered an explanation that extended Planck's idea. He proposed that light itself consists of discrete energy quanta. Each quantum carries energy equal to h on nu. When light strikes a metal surface, a single quantum transfers its energy to a single electron. If the energy exceeds the binding energy holding the electron in place, the electron is ejected. If not, nothing happens. This explained why frequency determined electron energy. Higher frequency meant higher energy per quantum. It explained why intensity controlled the number of emitted electrons. More intensity meant more quanta striking the surface. It also explained the absence of delay. Energy was transferred in one step, not accumulated gradually. Einstein's proposal was radical. It implied that the electromagnetic wave was not the whole story. Light sometimes behaved as if it were made of particles. At first, many physicists were skeptical. The wave theory had been so successful that abandoning it seemed unreasonable, but further experiments reinforced the particle-like aspects of light. One such experiment involved Compton scattering, discovered in 1923 by Arthur Compton. When X-rays scatter off electrons, the scattered radiation exhibits a shift in wavelength that depends on the angle of scattering. This effect can be explained by treating light as particles colliding with electrons, conserving energy and momentum. The calculations match the data precisely when photons are assigned momentum equal to E over c, where E is their energy and c is the speed of light. A purely classical wave treatment cannot account for the observed wavelength shift in this way. By this point, the evidence was overwhelming. Light could not be described solely as a continuous wave. It displayed particle-like properties in certain interactions. But the situation was not simple. Even as experiments demonstrated the particle-like behavior of light, other experiments continued to confirm wave-like properties. The double-slit experiment, for instance, produced interference patterns even when light intensity was so low that photons were sent through the apparatus one at a time. This created a conceptual problem. If light consists of particles, how can individual particles produce an interference pattern? If light is a wave, how can it transfer energy in discrete packets? The resolution came through the development of quantum mechanics in the 1920s. Rather than forcing light into the category of wave or particle, physicists introduced a new framework in which the wave function describes probabilities, and quantized interactions account for discrete energy transfer. In this framework, a photon is neither a classical particle nor a classical wave. It is a quantum object described by a probability amplitude that evolves according to wave equations, but produces localized detection events. This shift in thinking marked the true birth of the photon as a fundamental entity. The photon was not simply a tiny classical particle. It was the quantized excitation of the electromagnetic field, consistent with both wave-like propagation and particle-like interactions. As quantum theory developed further, the mathematical structure behind photons became clearer. In quantum electrodynamics, the electromagnetic field is quantized. The field can exist in discrete energy states. Each unit of excitation corresponds to a photon. The theory predicts not only the photoelectric effect and Compton scattering, but also subtle corrections to atomic energy levels and electron magnetic moments. These predictions have been verified to extraordinary precision, sometimes matching experiments to more than 10 decimal places. The birth of the photon was not a single event, but a gradual realization forced by experimental evidence. It required abandoning the assumption that energy is always continuous. It required accepting that nature at small scales does not conform to classical categories. It also required rethinking what it means to ask what something is made of. Before quantum mechanics, composition implied internal structure made of smaller classical parts. After quantum mechanics, fundamental entities could be excitations of fields with no smaller mechanical pieces. The photon emerged not as a miniature billiard ball, but as the smallest possible unit of electromagnetic excitation. The resistance of light to classical categorization was not a minor inconvenience. It signaled that the underlying structure of reality differs from everyday intuition. Light refused to behave according to established rules, and in doing so, it forced physics into a deeper theory. The implications extended beyond light itself. If electromagnetic radiation is quantized, perhaps other fields are as well. Indeed, the development of quantum field theory generalized the concept. Electrons, quarks, and other particles are also excitations of their respective fields. The photon was the first clear example that the classical wave description was incomplete. It became the prototype for understanding all other quantum particles. One additional feature solidified its status. Photons are bosons with spin equal to 1. They obey Bose-Einstein statistics, meaning multiple photons can occupy the same quantum state. This explains phenomena such as lasers, in which enormous numbers of photons share identical frequency and phase, producing coherent light. The laser is itself a practical demonstration of quantization. Stimulated emission causes atoms to emit photons that match the incoming photons exactly. The process depends on the discrete nature of energy levels in atoms and the quantized character of the electromagnetic field. None of this could be explained within purely classical wave theory. As the 20th century progressed, experiments continued to probe photon behavior at increasingly small scales and high precision. No evidence emerged of internal substructure. Photons behaved as elementary excitations, with properties determined by symmetry principles and conservation laws. The transition from wave to photon was not a rejection of Maxwell's equations, but an extension of them. The classical equations remain valid as a large-scale approximation, but at the quantum level, the field's energy is quantized, and those quanta are photons. Light refused to behave as a purely classical wave. It also refused to behave as a classical particle. The solution was not to choose one description over the other, but to recognize that both are limited approximations of a deeper quantum reality. Understanding that shift is essential before moving further into the question of composition. Because once we accept that photons are quantized excitations rather than composite objects, the question of what they are made of becomes less about internal parts and more about the structure of the field they arise from. From here, the focus naturally turns to the role of Einstein's proposal and how his interpretation of light as quanta reshaped the foundations of physics beyond the specific experiments that first revealed the photon's existence. By the early 20th century, physics stood at an uneasy crossroads. Maxwell's electromagnetic theory had unified electricity, magnetism, and light into one elegant system. The equations worked. The predictions matched experiment after experiment. On the surface, light was understood, and yet small cracks had begun to appear. The ultraviolet catastrophe had exposed a flaw in classical thermodynamics when applied to radiation. Planck's quantization had fixed the math, but few believed it described physical reality. The photoelectric effect was even more unsettling. It did not merely tweak an equation, it contradicted the core assumption that light's energy was continuous. Into this environment stepped Albert Einstein in 1905, during what would later be called his annus mirabilis, his miracle year. At the time, he was not a professor at a prestigious university. He was working as a patent clerk in Bern. Yet in that year he published a series of papers that reshaped physics. One of those papers addressed the photoelectric effect. In it, Einstein made a proposal that many of his contemporaries considered extreme. He suggested that light itself is quantized, not just the interaction between light and matter, light itself. This was not a small modification. Maxwell's equations describe light as a wave, smooth, continuous, spreading through space. Einstein proposed that, under certain conditions, light behaves as if it consists of localized energy packets. Each packet carries energy equal to Planck's constant multiplied by the frequency of the light. What made this proposal radical was that it seemed to undermine the very foundation of classical electromagnetism. If light were composed of particles, how could it produce interference patterns? How could it exhibit diffraction and polarization so clearly associated with waves? Einstein did not deny the wave behavior. Instead, he argued that light possesses a dual character. In processes of emission and absorption, it behaves as if energy is concentrated in discrete quanta. To understand how bold this was, consider the intellectual climate of the time. The wave theory of light had triumphed over Newton's earlier particle theory in the 19th century. Experiments like Thomas Young's double-slit experiment and Augustin-Jean Fresnel's diffraction studies had demonstrated beyond doubt that light exhibits wave-like properties. The idea of returning to a particle concept seemed like a step backward. But Einstein was guided by experimental evidence, not by allegiance to theory. The photoelectric effect was clear. The energy of ejected electrons depended only on frequency. Increasing intensity increased the number of electrons, not their individual energies. The simplest explanation was that each electron absorbs energy from a single quantum of light. Einstein's equation for the photoelectric effect was straightforward. The kinetic energy of the ejected electron equals the energy of the photon minus the work function of the metal, which is the energy required to remove the electron. This equation matched experimental data precisely. Even so, acceptance was slow. Many leading physicists viewed the light quantum as a useful mathematical device, not a real entity. Max Planck himself, despite introducing the constant that bears his name, was skeptical of Einstein's interpretation. Niels Bohr initially resisted the idea as well. The resistance was understandable. If light consisted of particles, what was their nature? Did they have mass? Did they have size? How could they travel at the speed of light? Einstein did not yet have the full framework of quantum field theory. He was working within the early stages of quantum mechanics, but his proposal planted a seed that would grow over the next 2 decades. One important development came from experiments on Compton scattering. When X-rays scatter off electrons, the change in wavelength depends on the scattering angle. The data fit perfectly with a particle model, in which photons carry momentum equal to their energy divided by the speed of light. Momentum without mass was another radical idea. In classical mechanics, momentum is mass times velocity. But for photons, momentum is linked to energy and frequency. This required rethinking basic concepts about motion and inertia. Einstein's own theory of special relativity, published in the same year as his photoelectric paper, played a crucial role here. Special relativity showed that energy and momentum are deeply connected. The famous equation E equals mc squared expresses the equivalence of mass and energy. For photons, which have zero rest mass, energy is entirely associated with motion. Their momentum arises from their energy and the fact that they travel at the universal speed limit. Relativity made it possible to understand how a massless particle could still carry momentum. This reinforced the reality of the photon. Einstein's proposal also had implications for atomic structure. If light is quantized, then atoms must absorb and emit energy in discrete amounts. This aligned with observations of atomic spectra, where atoms emit light at specific frequencies corresponding to transitions between quantized energy levels. Over time, the concept of the photon became inseparable from the developing theory of quantum mechanics. The wave function, introduced by Schrödinger and others, described probabilities of outcomes, but energy exchange occurred in discrete units. The term photon itself was introduced later, in 1926, by chemist Gilbert Lewis. Einstein had referred to light quanta. The new name helped solidify the concept as a particle-like entity within the growing framework of quantum theory. It is worth emphasizing how conceptually disruptive this was. The classical world allowed for clear categories. Objects were particles, disturbances were waves. A stone thrown into water was not also a wave. A water wave was not also a particle. Quantum objects refused to fit these categories. A photon could produce interference patterns like a wave, but transfer energy in discrete packets like a particle. The old language was inadequate. Einstein's proposal forced physicists to accept that nature at small scales does not conform to classical intuition. It introduced the idea that energy, once thought infinitely divisible, comes in fundamental units. That idea extended beyond light. Soon, matter itself was found to exhibit wave-like properties. Louis de Broglie proposed that particles such as electrons have wavelengths associated with them. Experiments confirmed electron diffraction, showing that the wave-particle duality was not unique to light. In hindsight, Einstein's radical proposal was a stepping stone toward a much broader principle. Quantization is a universal feature of nature at small scales. For our central question, what a photon is made of, Einstein's work narrows the possibilities. If photons are fundamental quanta of the electromagnetic field, then they are not composed of smaller classical pieces. Their existence is tied directly to the quantization of that field. Einstein did not provide the final mathematical framework for photons. That would come later with quantum electrodynamics, but he established their necessity. Without discrete light quanta, the experimental data could not be explained. It is also interesting that Einstein himself later expressed discomfort with certain aspects of quantum theory, particularly its probabilistic interpretation. Yet his work on light quanta was one of the key contributions that launched the quantum revolution. The radical nature of his proposal lay not only in its content, but in its philosophical implications. It suggested that energy exchange at the smallest scales is inherently discrete. It implied that continuity, so central to classical physics, is not fundamental. Photons are not small fragments chipped off a continuous wave. They are the smallest indivisible units of electromagnetic energy permitted by nature. As experiments became more precise, the particle-like properties of photons were confirmed again and again. Yet their wave-like aspects remained equally undeniable. The duality was not a flaw to be corrected, but a feature to be understood. Einstein's proposal did not answer every question about photons. It did not specify whether they had internal structure or deeper constituents. But it did establish that any satisfactory theory must treat light as quantized. From that point onward, asking what a photon is made of required stepping into the language of quantum fields rather than classical mechanics. The photon was no longer a conceptual convenience. It was a fundamental entity demanded by experiment, and once that shift was accepted, attention turned toward understanding how such an entity could simultaneously exhibit wave-like propagation and particle-like interaction, a question that would lead directly into the deeper structure of quantum theory itself. By the time quantum theory began to take shape in the 1920s, the photon was no longer a controversial guess. It had become a necessary part of the description of light. But what it actually was remained unclear. If it was not a classical particle, and not merely a classical wave, then what exactly did quantum theory say it was? To answer that, we have to move carefully into the framework that replaced classical mechanics and classical electromagnetism at small scales. Quantum theory did not simply add a few corrections to old equations, it changed the conceptual foundation. In classical physics, a particle has a definite position and momentum at all times. A wave is a continuous disturbance described by amplitudes that vary smoothly through space. These categories are mutually exclusive. A particle is localized. A wave is spread out. Quantum theory introduced a new object, the wave function. The wave function does not describe a physical wave in the classical sense. It describes a probability amplitude. From it, we can calculate the likelihood of detecting a particle at different positions or with different momenta. For photons, the situation is slightly more subtle than for particles like electrons. Photons are excitations of the electromagnetic field, so their full description belongs to quantum field theory, rather than to the simpler non-relativistic quantum mechanics used for electrons in atoms. But the core idea is similar. In quantum field theory, every type of particle corresponds to a field that exists everywhere in space. There is an electron field, a quark field, and an electromagnetic field. The photon is the quantum of the electromagnetic field. What does that mean in precise terms? It means that the electromagnetic field can exist in discrete energy states. In classical electromagnetism, the field's energy can vary continuously. In quantum theory, the field's energy at a given frequency comes in multiples of a basic unit. That unit is one photon. If the field at a certain frequency has 0 photons, it is in its ground state for that mode. If it has 1 photon, it is in the first excited state. 2 photons correspond to the second excited state, and so on. The number of photons in a particular mode is quantized. This is not just a mathematical label. It has measurable consequences. When a photon is absorbed by an atom, the atom's energy increases by exactly 1 quantum of energy equal to h nu. The electromagnetic field loses 1 excitation at that frequency. The language of quantum theory describes this process using operators called creation and annihilation operators. A creation operator adds 1 photon to a particular mode of the field. An annihilation operator removes 1 photon. These operators act on quantum states in a well-defined way. From this perspective, a photon is not a tiny object with spatial extent and internal structure. It is a change in the state of the electromagnetic field. This may seem abstract, but it has precise mathematical content. The electromagnetic field is described by field operators that satisfy specific commutation relations. When the field is quantized, its energy spectrum becomes discrete. Each discrete unit corresponds to a photon. The photon has specific properties determined by the symmetries of the electromagnetic field and space-time. It has spin equal to 1 unit of angular momentum. It has 2 polarization states in free space. It has 0 rest mass. It always travels at the speed of a light in vacuum. These properties are not assigned arbitrarily. They emerge from the mathematical structure of the theory. The requirement of gauge invariance, symmetry under certain transformations of the field, leads directly to the existence of a massless spin-1 particle. That particle is the photon. Gauge invariance is a deep principle in modern physics. In quantum electrodynamics, the theory describing interactions between charged particles and photons, local gauge symmetry, ensures conservation of electric charge. The photon arises naturally as the force carrier associated with this symmetry. This is an important point. The photon is not just a packet of energy. It is the mediator of the electromagnetic force. When 2 charged particles interact, they exchange photons. In the quantum field description, this exchange can be represented by diagrams showing virtual photons connecting interaction points. Virtual photons are not directly observable particles. They are internal lines in the mathematical description of interactions, but they illustrate how the electromagnetic force operates at the quantum level. The fact that photons mediate the electromagnetic force further supports their fundamental status. If they had internal structure, that structure would likely affect the form of electromagnetic interactions. So far, experiments show no such deviations. Another aspect of quantum theory clarifies the photon's wave-particle behavior. The photon's wave function spreads out in space according to Maxwell's equations when considered at large scales. But when a measurement occurs, when a photon is detected, the result is a localized event. Quantum theory does not describe the photon as traveling along a single definite path between emission and detection. Instead, it provides a probability distribution for possible detection outcomes. The act of measurement yields a specific result. In the double-slit experiment with single photons, each photon is described by a probability amplitude that passes through both slits. The interference pattern arises from the superposition of these amplitudes, but each detection event is localized at a single point on the screen. This is not because the photon splits into smaller pieces and recombines. It is because the quantum state evolves as a superposition, and detection collapses that state into a specific outcome. Importantly, quantum theory does not require that the photon be composed of smaller constituents to exhibit this behavior. The probabilistic nature arises from the mathematical structure of the wave function and field operators. We can also ask about the photon's spatial extent. Does it have a size? In quantum field theory, a photon does not have a fixed classical size. Its spatial distribution depends on the state in which it is prepared. A photon emitted by an atom may have a wave packet extending over a large region of space, but this does not mean it is physically spread out as a tiny object with boundaries. It means the probability amplitude for detection extends over that region. If we try to localize a photon very precisely, its momentum becomes uncertain, according to the Heisenberg uncertainty principle. This trade-off between position and momentum uncertainty is not a sign of internal structure. It is a fundamental feature of quantum states. The question of what a photon is made of becomes less meaningful within this framework. A photon is defined as the smallest excitation of a field that itself is considered fundamental in the Standard Model. There are no smaller field quanta inside it. Of course, physics does not claim final knowledge. It is possible that future theories, such as those attempting to unify gravity with quantum mechanics, may reveal deeper layers. Some speculative theories suggest that all particles, including photons, could be manifestations of vibrating strings or other fundamental entities, but there is currently no experimental evidence supporting substructure within the photon. Within the established framework of quantum electrodynamics, the photon is elementary. Its properties are fixed by symmetry principles and the quantization of the electromagnetic field. It is also worth noting how successful this theory has been. Quantum electrodynamics predicts the behavior of photons and electrons with extraordinary precision. The agreement between theory and experiment for quantities such as the anomalous magnetic moment of the electron is one of the most accurate matches in all of science. If photons had hidden internal components, we would expect small deviations from the predictions of quantum electrodynamics at high energies. Extensive experiments have searched for such deviations and found none so far. So according to quantum theory, a photon is not made of smaller particles. It is not a composite object. It is a fundamental excitation of a quantized field. Its energy is determined by its frequency. Its momentum is related to that energy. Its spin and polarization arise from the structure of the electromagnetic field and the symmetries of space-time. This answer may feel less tangible than saying something is made of tiny pieces, but it's more precise. The photon's identity is defined by its role in the theory and by the measurable properties it exhibits. And once we accept that description, the natural question becomes how to reconcile this quantum object with the intuitive categories of particle and wave that still influence how we talk about light. Because even though quantum theory provides a formal definition, the tension between those classical categories has not entirely disappeared. By this point, we have two descriptions of light that both work, and yet they seem to contradict each other. In one description, light is an electromagnetic wave, a continuous oscillation of electric and magnetic fields spreading smoothly through space. In another, light is made of photons, discrete quanta that transfer energy in indivisible packets. So which is it? Is a photon a particle? Is it a wave? Or is it something that does not fit into either category? The difficulty begins with the words themselves. Particle and wave are classical concepts. They come from everyday experience. A particle is something localized. It has a position. It can collide with other objects. A wave is something extended. It spreads out. It can interfere with itself. In classical physics, these categories are mutually exclusive. A billiard ball does not produce interference patterns by passing through two openings simultaneously. A water wave does not strike a detector at a single point with all its energy concentrated there. Photons do both. When light passes through a double-slit apparatus and produces an interference pattern, it behaves in a way that is unmistakably wave-like. The pattern cannot be explained by imagining tiny bullets passing independently through one slit or the other. The interference fringes arise from the superposition of probability amplitudes associated with both paths. At the same time, when light interacts with matter, it does so in discrete events. A single photon can eject a single electron in the photoelectric effect. A detector registers a localized click. Energy arrives in packets that cannot be subdivided. If we insist on using classical language, we are forced into awkward statements like, light is both a particle and a wave. But that phrasing suggests that the photon somehow alternates between two modes of being, switching roles depending on the experiment. That is not what quantum theory says. Quantum theory does not describe the photon as half particle and half wave. It describes it as a quantum excitation whose behavior is governed by a mathematical object called a state vector or wave function. This state evolves continuously and can interfere with itself like a wave, but the outcomes of measurements are discrete, like particle detections. The wave-like aspect refers to the evolution of probability amplitudes. The particle-like aspect refers to the quantized nature of interactions. To understand this more concretely, consider again the double-slit experiment performed with single photons. Photons are emitted one at a time. Each detection on the screen appears as a single localized spot. No individual photon creates a full interference pattern by itself. Instead, the pattern emerges statistically as many detection events accumulate. The wave function describing each photon spreads out and passes through both slits in a superposition of possibilities. The probability amplitude associated with each path combines, producing regions of higher and lower probability. But when a measurement occurs, only one outcome is realized. There is no classical analogue for this behavior. A classical particle travels along a definite path. A classical wave spreads continuously and deposits energy everywhere along its front. A photon does neither in a classical sense. One might ask whether the photon has a definite trajectory between emission and detection. Quantum theory does not assign it one. Instead, it provides a probability distribution for where it might be detected. The idea of a precise path becomes meaningless unless a measurement is made to determine it, and when such a measurement is performed, the interference pattern disappears. This phenomenon is sometimes described as complementarity, a concept introduced by Niels Bohr. The idea is that wave-like and particle-like descriptions are complementary aspects of a single underlying reality. Depending on how an experiment is set up, one aspect becomes apparent while the other is suppressed. But complementarity is not a statement about the photon changing its nature. It is a statement about how different experimental arrangements reveal different features of the same quantum object. Another way to approach the issue is through the concept of quantum fields. In quantum field theory, the electromagnetic field is fundamental. The photon is a quantized excitation of that field. The field itself is described by equations that resemble wave equations. So the wave aspect arises naturally from the field description. At the same time, the field's energy is quantized. It can exist only in discrete energy states. The smallest unit of excitation corresponds to one photon, so the particle aspect arises from quantization. In this sense, asking whether a photon is a particle or a wave may be the wrong question. It is neither in the classical sense. It is a quantum object described by a field whose excitations behave according to quantum rules. It is also useful to consider how photons behave in different contexts. In a laser beam, Enormous numbers of photons occupy the same quantum state. The collective behaviour can be described accurately by classical electromagnetic waves. In this regime, the wave picture is sufficient. In extremely low-intensity experiments involving single photon sources and detectors, the discrete nature becomes unavoidable. Here, the particle-like aspect dominates. The underlying theory does not change between these cases. What changes is the scale and the type of measurement being performed. Some interpretations of quantum mechanics attempt to assign a more concrete ontology to the photon. In pilot wave theories, for example, particles are guided by a wave function that determines their trajectories. In other interpretations, the wave function represents information rather than a physical wave. In still others, such as the many worlds interpretation, all possible outcomes coexist in a branching structure. Despite these interpretational differences, the formalism remains consistent. The photon is described by quantum states that evolve according to well-defined equations. Detection events are probabilistic but governed by precise mathematical rules. Another important feature to mention is that photons are indistinguishable particles. If two photons have the same frequency, polarization, and direction, there is no way to label them individually. Swapping them does not produce a new physical state. This indistinguishability is a purely quantum property and has no classical counterpart. Photons also obey Bose-Einstein statistics. This allows multiple photons to occupy the same quantum state, leading to phenomena such as coherent light in lasers and Bose-Einstein condensation in other systems of bosons. None of these behaviors fit neatly into the classical particle concept. A classical particle retains its identity and individuality. Photons do not have such individuality in the same sense. Likewise, the classical wave concept does not capture the quantized nature of energy transfer. A classical wave can deposit energy in arbitrarily small amounts. A photon cannot. So when we ask whether a photon is a particle or a wave, the most accurate answer is that it is something else entirely. A quantum of a field whose behaviour transcends classical categories. The discomfort that arises from this answer comes from the fact that human intuition is built on classical experiences. We have direct sensory access to particles like grains of sand and waves like ocean swells. We do not have direct sensory access to quantum fields. Quantum theory forces us to accept that classical analogies are limited. They can provide hints, but they cannot fully describe reality at small scales. Importantly, this does not mean that photons are mysterious in the sense of being unknowable. Their properties are precisely defined in the mathematical structure of quantum electrodynamics. We can calculate scattering probabilities, cross-sections, polarization effects, and interaction rates with remarkable accuracy. The confusion arises only when we try to translate those precise mathematical descriptions into everyday language built for macroscopic objects. In summary, a photon is not a classical particle travelling along a definite path, nor is it a classical wave spreading continuously through space. It is a quantum excitation of the electromagnetic field, whose evolution is wave-like in terms of probability amplitudes, and whose interactions are discrete in terms of energy exchange. Once we accept that, the focus shifts away from trying to categorize photons as familiar objects and toward understanding the specific properties they possess, such as energy, momentum, polarization, and spin, and how those properties arise from the structure of the field and the symmetries of space-time. One of the most striking properties of the photon is that it has no rest mass. That statement appears in textbooks as a simple fact. The photon's rest mass is exactly zero, as far as experiments can tell. But that fact immediately raises a question. If it has no mass, what does it actually have? What defines it physically? In classical mechanics, mass plays a central role. It measures inertia. It tells us how difficult it is to change an object's motion. It determines how strongly objects attract one another gravitationally. When we describe a particle, mass is usually one of the first numbers we assign to it. Photons do not fit that pattern. They have zero rest mass, yet they clearly exist, carry energy, exert forces, and produce measurable effects. They can push on objects, they can be detected individually, they can travel across billions of light years and still interact with matter when they arrive. So if mass is not what defines them, what does? The first and most fundamental property a photon has is energy. The energy of a photon is directly proportional to its frequency. The relationship is given by the formula E equals hh nu, where h is Planck's constant, and nu is the frequency of the light. This means that a photon of blue light carries more energy than a photon of red light. X-ray photons carry far more energy than visible photons. Radio wave photons carry much less. The difference between these forms of light is not in their composition, it is in their frequency, and therefore in their energy. Energy is not an abstract label, it has concrete consequences. When a photon is absorbed by an atom, the atom's energy increases by exactly that amount. If the photon's energy matches the difference between two energy levels in the atom, absorption can occur. If not, the photon passes by without interaction. The photon also has momentum. In classical physics, momentum is mass times velocity. For photons which have zero rest mass, the relationship is different. Their momentum is given by P equals E over c, where E is energy and c is the speed of light. This means that even without mass, photons carry momentum proportional to their energy. This momentum can be transferred to matter. When light strikes a surface, it exerts radiation pressure. This effect has been measured experimentally and is used in theoretical designs for solar sails that could be propelled through space by sunlight alone. The existence of photon momentum also explains phenomena like Compton scattering. When a photon collides with an electron, both energy and momentum are conserved. The change in wavelength of the scattered photon depends on the angle of collision, and the equations match observations precisely when photon momentum is included. So even though photons have no rest mass, they have energy and momentum. These quantities are linked by the principles of special relativity. In special relativity, mass is not the only way to describe energy content. The total energy of a particle depends on both its rest mass and its motion. For particles with non-zero rest mass, energy includes a rest energy component mc². For photons, the rest mass term is zero, but the energy associated with motion remains. Another property photons have is spin. Spin is a form of intrinsic angular momentum. It is not the result of physical spinning in space, as a classical object might spin. Instead, it is a quantum property that arises from how the particle transforms under rotations. Photons have spin equal to 1 unit in quantum mechanical terms. Because they are massless, only 2 spin states are physically realized, corresponding to 2 possible polarizations. These are often described as left-handed and right-handed circular polarizations. Polarization is something we can observe directly. Polarizing filters, for example, allow only certain orientations of the electric field to pass through. This corresponds to selecting photons in a particular polarization state. The fact that photons have spin is not trivial. It influences how they interact with matter and how they are described in quantum field theory. The electromagnetic field must have the correct mathematical structure to produce a massless spin 1 particle. This requirement ties directly into the symmetry principles of the theory. Another property photons have is that they are electrically neutral. They carry no electric charge. This is important because it means they do not interact directly with one another under ordinary conditions. Charged particles respond to electromagnetic fields. Photons are the carriers of that field, so they do not carry charge themselves. The neutrality of photons also means that they can travel long distances without being deflected by electric or magnetic fields. This is why light from distant stars can cross vast stretches of space largely unimpeded. Photons also obey Bose-Einstein statistics. They are bosons. This means that multiple photons can occupy the same quantum state. There is no exclusion principle preventing them from sharing identical properties. This allows coherent light sources like lasers to function, with large numbers of photons in the same state. All of these properties — energy, momentum, spin, polarization, neutrality, bosonic behavior — define what a photon is in physical terms. None of them require internal structure. They arise from the mathematical description of the electromagnetic field and the symmetries of space-time. It is also important to understand what massless really implies in relativity. For a particle with non-zero rest mass, there exists a reference frame in which the particle is at rest. For a photon, there is no such frame. It always travels at the speed of light in vacuum. There is no way to slow down a photon to rest. This is not a limitation of technology. It is a fundamental feature of space-time structure. The equations of relativity show that any massless particle must travel at exactly c in vacuum. Its speed is not adjustable. This also means that photons experience no passage of proper time between emission and absorption. From the perspective of relativity, the interval along a light-like path is zero. This does not mean that photons have consciousness or a frame of reference. It means that within the mathematical structure of space-time, the proper time along their trajectory is zero. Another consequence of being massless is that photons are long-range force carriers. In quantum field theory, the mass of a force-carrying particle determines the range of the force it mediates. A massless mediator produces a force with infinite range, decreasing with distance but never cutting off completely. This is why the electromagnetic force extends over large distances. In contrast, the weak nuclear force is mediated by massive particles called W and Z bosons. Their large mass limits the range of the weak interaction to extremely short distances. So even though photons have no rest mass, they play a central role in shaping the structure of the universe. Their properties determine how charged particles interact, how light propagates, and how energy moves through space. If we return to the original question, if it has no mass, what does it have? The answer is that it has precisely the properties required by the symmetries of the electromagnetic field and the structure of space-time. It has quantized energy determined by frequency. It has momentum proportional to that energy. It has intrinsic spin corresponding to polarization states. It has no electric charge. It travels at a fixed speed. None of these properties depend on being composed of smaller pieces. They are fundamental characteristics. When we encounter an object in everyday life, we often define it by what it is made of. But in quantum field theory, fundamental particles are defined by how they behave under transformations, how they respond to rotations, translations, and gauge symmetries. The photon is defined by these transformation properties. It is the massless spin of one quantum of the electromagnetic field. That description captures everything we have been able to measure about it so far. And once we recognize that, the next question naturally becomes whether a photon possesses any internal spatial structure at all, or whether it is truly point-like in every measurable sense. If we strip the photon down to what can be measured most directly, we arrive at a simple but powerful relationship. Energy and frequency are inseparable. The energy of a photon is not an arbitrary value. It is fixed by its frequency through the equation E equals h nu. This equation is not just a definition. It is one of the most fundamental statements in quantum physics. It tells us that electromagnetic energy does not come in continuous amounts. It comes in discrete packets, whose size depends on how rapidly the electromagnetic field oscillates. To understand why this matters, it helps to contrast it with the classical picture once more. In classical electromagnetism, the energy carried by a wave depends on its amplitude. A wave with larger amplitude carries more energy, but there is no smallest unit of energy in that description. You can imagine reducing the amplitude indefinitely, producing waves with arbitrarily small energy. Quantum theory changes that. For a given frequency, there is a minimum possible amount of energy that can be transferred: one photon. You cannot have half of that minimum in a single interaction. You can have 0 photons, 1 photon, 2 photons, and so on, but you cannot have 0.3 photons being absorbed by an atom. This discreteness is not a technical limitation of measurement. It is built into the structure of the electromagnetic field when it is quantized. The field's energy levels are separated by steps of size h and u. Planck's constant, h, sets the scale of this quantization. Its value is extremely small in everyday units, approximately 6.626 times 10 to the power of minus 34 joule-seconds. Because it is so small, quantum effects are usually negligible at macroscopic scales. But at atomic scales, that constant governs the behavior of energy exchange. The frequency nu determines how much energy each photon carries. High-frequency radiation such as gamma rays consist of photons with very large energy per packet. Low-frequency radiation such as radio waves consists of photons with very small energy per packet. It is important to recognize that intensity and frequency are separate concepts. Intensity corresponds to the number of photons arriving per unit time and area. Frequency determines the energy of each photon. Increasing the brightness of red light increases the number of red photons. It does not change the energy per photon. This distinction explains the photoelectric effect. If the frequency is below a certain threshold, no electrons are ejected regardless of intensity. Increasing intensity only increases the number of low-energy photons, not their individual energies. Only photons with sufficient frequency, and therefore sufficient energy per packet, can overcome the binding energy of electrons in the material. This leads to the idea that the photon is the smallest possible packet of electromagnetic energy at a given frequency. It is not made of smaller energy fragments that can be subdivided arbitrarily. In quantum field theory, this quantization arises naturally when the electromagnetic field is treated as a collection of harmonic oscillators, one for each mode of the field. Each oscillator can have energy levels separated by h nu. The ground state has energy 1/2 h nu, often called 0-point energy. The first excited state has energy 3/2 h nu, and so on. The difference between adjacent levels is exactly h nu. The presence of 0-point energy is another subtle feature. Even when there are no photons present, each mode of the field retains a residual energy of 1/2 h nu. This energy cannot be removed. It reflects the fact that quantum systems cannot have precisely zero motion, due to the uncertainty principle. However, when we talk about photons in practical terms, we usually focus on the excitations above the ground state. Each excitation corresponds to one photon. The discreteness of photon energy has measurable consequences beyond the photoelectric effect. It explains atomic emission spectra. When an electron in an atom transitions from a higher energy level to a lower one, it emits a photon whose energy equals the difference between those levels. The frequency of the emitted light is therefore fixed by that energy difference. This produces spectral lines characteristic of each element. These lines are not continuous bands. They occur at specific frequencies corresponding to allowed energy transitions. The existence of sharp spectral lines was one of the earliest clues that atomic energy levels are quantized. The smallest possible packet of light at a given frequency is not just a conceptual unit, it is the building block of all electromagnetic radiation. Another example appears in lasers. In a laser, atoms are stimulated to emit photons coherently. The process depends on the fact that energy exchange occurs in discrete quanta. Stimulated emission ensures that emitted photons match the frequency, phase, and direction of incoming photons. The coherence of laser light arises from this quantized interaction. The relationship between energy and frequency also connects to temperature and thermal radiation. The distribution of photon energies emitted by a hot object follows Planck's law. At higher temperatures, the peak of the distribution shifts toward higher frequencies, meaning higher energy photons become more common. In astrophysics, the quantized nature of photons allows scientists to determine the composition and temperature of distant stars. By analysing the frequencies of emitted or absorbed photons, we can infer atomic transitions occurring billions of kilometres away. The frequency of a photon is also tied to its wavelength by the relation c equals lambda nu, where c is the speed of light and lambda is the wavelength. Combining this with E equals h nu gives another useful expression, E equals hc over lambda. This shows that shorter wavelengths correspond to higher energy. This relationship explains why ultraviolet radiation can cause chemical damage to biological tissue, while visible light generally cannot. The photon energy at higher frequencies is sufficient to break molecular bonds. The idea of the photon as the smallest packet of electromagnetic energy also clarifies what happens during attenuation. When light passes through a material and becomes dimmer, the process involves some photons being absorbed or scattered. The amplitude of the classical wave decreases because fewer photons remain. The energy is reduced in discrete steps, not continuously shaved down within individual photons. We might ask whether there is any smaller subdivision possible under extreme conditions. Experiments have tested photon interactions at very high energies. So far, there is no evidence that photons can fragment into smaller energy units, in the way composite particles can break apart into constituents. This does not mean photons are indestructible. They can transform under certain conditions. For example, a high-energy photon passing near a nucleus can produce an electron-positron pair. But this process does not split the photon into smaller photons. It converts the photon's energy into mass consistent with relativity. The threshold energy for such pair production is determined by the rest mass energy of the electron and positron. Below that energy, the process cannot occur. Above it, energy can transform into matter. This demonstrates another crucial feature. Photon energy is convertible into mass and vice versa. The photon's energy content is not merely an abstract quantity. It is interchangeable with mass according to E equals mc squared. Despite having no rest mass, photons are deeply integrated into the energy structure of the universe. Their energy is real and measurable. Their frequency determines the size of the quantum of energy they carry. That quantum cannot be subdivided within a single interaction. When we speak of the smallest possible packet, we are not imposing a limitation of technology or resolution. We are describing a fundamental property of the quantized electromagnetic field. At everyday scales, this discreteness is invisible because the number of photons involved is enormous. A typical light bulb emits roughly 10 to the power of 20 photons per second. The individual quanta blend into what appears as continuous illumination. But at low intensities or in carefully controlled experiments, the discrete nature becomes unavoidable. Photodetectors register individual events. Atoms absorb and emit energy one quantum at a time, so when we ask what a photon has, one central answer is that it has energy tied rigidly to frequency. It has the smallest possible unit of electromagnetic energy permitted by quantum mechanics. And once we accept that, it naturally leads to another question. If energy comes in discrete packets determined by frequency, does that imply that a photon has a definite size or shape in space, or is its spatial character governed by entirely different principles? When we picture a particle in everyday terms, we imagine something with boundaries. A grain of sand has a size, a marble has a shape. Even atoms, though unimaginably small, are often drawn as tiny spheres. So it is natural to ask whether a photon has a size or a shape. If it is a particle, does it occupy a small region of space like a point? If it is a wave, is it spread out over a certain distance? The short answer is that a photon does not have a fixed classical size or shape. But that statement needs careful unpacking, because it is easy to misunderstand what that means. In classical physics, size refers to spatial extension. An object has a definite radius or length. It can be measured directly. Its boundaries separate it from empty space. Photons do not fit that description. In quantum theory, the photon is described by a quantum state. That state can be localized to varying degrees, But the localization is not the same as having a rigid physical boundary. Instead, what we talk about is the spatial distribution of the probability amplitude for detecting the photon. If a photon is prepared in a certain way, say, emitted by an atom during a transition, it will be described by a wave packet. A wave packet is a superposition of many plane waves with slightly different wavelengths. The result is a localized distribution in space, meaning the probability of detecting the photon is concentrated within a certain region, but that region is not a hard-edged object. It is a region where the detection probability is significant. Outside that region, the probability gradually falls off but does not abruptly become zero. In principle, the spatial extent of a photon wave packet can be very large. For example, light emitted from a distant star can consist of photons whose wave packets extend over enormous distances by the time they reach Earth. The photon is not a tiny bead travelling intact across space. It is a quantum excitation whose spatial description can span kilometres or more depending on how it was produced. On the other hand, in laboratory conditions, photons can be engineered to have very short pulses. In ultrafast optics, scientists generate pulses lasting femtoseconds or even attoseconds. The spatial extent of such pulses corresponds to the distance light travels during that time interval. Even then, the concept of size refers to the length of the wave packet, not to a rigid object. Another important factor is the uncertainty principle. In quantum mechanics, position and momentum cannot both be known with arbitrary precision. The more precisely we try to localize a photon in space, the greater the uncertainty in its momentum and therefore in its frequency. This means that there is no such thing as a perfectly localized photon with a sharply defined frequency. A photon with a single precise frequency would correspond to an infinite plane wave extending throughout space. Conversely, a photon localized in a very small region must contain a spread of frequencies, so asking for a definite size independent of context is not meaningful. The photon's spatial extent depends on how it is described and how it is prepared. What about shape? In classical terms, shape implies geometry. A sphere, a cube, a rod. Photons do not have shape in that sense. They do not have a surface or internal volume. They are not solid objects with spatial boundaries. However, photons do have polarization states, and these can give rise to structured electromagnetic fields. For example, light beams can be shaped into patterns with specific spatial distributions, such as Gaussian beams, or more complex modes carrying orbital angular momentum. These structured beams have particular field profiles, but those profiles describe the electromagnetic field configuration, not the shape of an individual photon as a tiny object. When a single photon is prepared in a particular spatial mode, its quantum state reflects that mode. The probability amplitude for detection mirrors the structure of the field configuration. But again, this is not the same as saying the photon has a geometric shape. Experiments at high energies also provide insight. Particle accelerators probe the structure of particles by colliding them at extremely high energies. If a particle has internal structure, scattering experiments reveal deviations from point-like behavior. For example, protons were once thought to be fundamental, but high-energy scattering experiments showed that they contain quarks. Similar experiments have been conducted to test whether photons exhibit any substructure. So far, all results are consistent with the photon behaving as a point-like particle in interactions. There is no evidence of internal spatial extent in the sense of composite structure. This does not mean that the photon is a tiny solid point occupying zero volume in a classical sense. Rather, it means that when it interacts, it behaves as if it has no internal components and no measurable size. In quantum field theory, particles are often treated as point-like excitations. The electromagnetic field exists everywhere in space. A photon corresponds to a specific excitation of that field. The field itself has values at every point in space, but the excitation is described in terms of quantum states rather than classical spatial objects. Another way to approach the question is through wavelength. The wavelength of light is related to its frequency by the equation lambda equals c over nu. This wavelength determines many observable properties, such as interference patterns and diffraction limits. It is tempting to equate wavelength with size, but wavelength is not the physical size of a photon. It is the spatial period of the oscillating electromagnetic field. A photon with wavelength 500 nanometers does not have a diameter of 500 nanometers. The wavelength characterizes the oscillatory behavior of the field, not the extent of a tiny object. In fact, as mentioned earlier, a photon described by a single precise wavelength corresponds mathematically to an infinitely extended plane wave. Real photons are described by wave packets that combine many wavelengths. In certain quantum optics experiments, researchers manipulate the temporal and spatial profiles of single photons. These experiments demonstrate that photons can be shaped in terms of their probability distributions and field modes. Yet this shaping refers to the structure of the electromagnetic field configuration associated with the photon, not to a rigid geometric form. It is also useful to consider what happens during detection. When a photon is absorbed by a detector, the event occurs at a localized point. The energy transfer is concentrated. The detection does not occur gradually across an extended object. It is a discrete event. This localized detection might suggest that the photon was localized prior to detection, but quantum theory does not require that interpretation. The localization arises at the moment of interaction. Before that, the photon state may have been spatially extended. All of this points to a broader conclusion. The photon does not have size or shape in the classical sense. Its spatial characteristics are determined by its quantum state. That state can be more or less localized depending on how the photon is prepared and measured. If future experiments were to reveal deviations from point-like behavior at extremely high energies, that would indicate internal structure. So far, no such evidence exists. Within the standard model, the photon is treated as elementary and without substructure. So when we ask whether a photon has size or shape, the most accurate answer is that these concepts do not apply in the way they do for everyday objects. The photon's identity is not defined by geometry, but by its quantum properties: energy, momentum, spin, and polarization. And once we let go of the idea that it must have classical dimensions, the next natural step is to examine more closely the deeper framework that gives rise to these properties in the first place, the quantum fields from which photons emerge. When we ask what something is made of, we are usually asking what lies inside it. Atoms contain nuclei and electrons. Nuclei contain protons and neutrons. Protons and neutrons contain quarks. Each layer, once thought fundamental, turned out to have internal structure when examined closely enough, so it is reasonable to ask whether the same might be true for the photon. If we could probe it with enough precision, would we find smaller constituents inside? Or is the photon truly elementary? To approach this question, we need to understand how physicists look inside a particle in the first place. We do not open particles the way we might cut open a physical object. Instead, we study how they behave in high-energy collisions. When particles scatter off one another, the patterns of scattering reveal information about their internal structure. If a particle has substructure, collisions at sufficiently high energies can resolve it. For example, early experiments treated protons as indivisible, but when electrons were accelerated to very high energies and fired at protons, the scattering data showed that the proton was not uniform inside. The patterns revealed point-like constituents, quarks, within it. This technique relies on the fact that higher energies correspond to shorter wavelengths. A particle used as a probe has an associated wavelength inversely proportional to its momentum. To resolve smaller structures, you need shorter wavelengths, which require higher energies. So the question becomes, have we performed experiments energetic enough to probe inside the photon? And if so, what did we find? High-energy particle accelerators, such as those at CERN, routinely study interactions involving photons. Photons participate in scattering processes, pair production, and other high-energy events. If photons had internal components, those components would likely influence these interactions in measurable ways. So far, all experimental evidence indicates that photons behave as point-like particles with no detectable internal structure. Their interactions match the predictions of quantum electrodynamics with extraordinary precision. There are no deviations suggesting subparticles or composite behavior. This does not mean that it is logically impossible for photons to have deeper structure. It means that within the range of energies we have explored, no such structure has been observed. In the standard model of particle physics, the photon is classified as an elementary gauge boson. Elementary means it is not composed of smaller particles within the framework of the theory. Gauge boson means it arises from a fundamental symmetry, specifically the U1 gauge symmetry associated with electromagnetism. The properties of the photon are dictated by this symmetry: its masslessness, its spin, its polarization states. These are not arbitrary features. They follow from the mathematical structure of the gauge theory. If the photon were composite, its properties would likely differ slightly from the exact predictions of the standard model. For example, its interactions might vary at extremely high energies. Experiments searching for such deviations have placed very tight limits on possible substructure. There are, however, speculative theories that go beyond the standard model. Some versions of string theory propose that what we call particles are actually tiny vibrating strings. In that picture, the photon would correspond to a particular vibrational mode of a fundamental string. If string theory were correct, then photons would not be made of smaller particles in the traditional sense. Instead, they would be manifestations of a deeper underlying object. But string theory remains unconfirmed. There is no experimental evidence yet that particles are strings. Other speculative models consider the possibility that spacetime itself has a discrete structure at extremely small scales, perhaps near the Planck length, about 1.6 times 10 to the power of minus 35 meters. At that scale, quantum gravity effects may become important. If spacetime has a granular structure, then the behavior of photons at extremely high energies might reveal it. So far, however, no experiment has reached the Planck scale. The energies required are far beyond current technological capabilities. Within accessible energy ranges, photons appear structureless. There is also an important conceptual distinction to make. Even if a photon is elementary in the standard model, it can still participate in complex interactions. For example, a high-energy photon can fluctuate temporarily into a virtual electron-positron pair. This process is allowed by quantum mechanics as long as it respects energy-time uncertainty constraints. In such cases, the photon is not permanently composed of an electron and positron. Rather, the quantum field allows transient fluctuations that influence scattering processes. These fluctuations contribute to measurable effects, such as vacuum polarization. But these virtual processes do not imply that the photon has internal components in the way a proton contains quarks. They are temporary features of the quantum field, not constituent building blocks. One way physicists test for internal structure is by measuring form factors, quantities that describe how a particle's internal distribution affects scattering. For composite particles, form factors deviate from those expected for point-like objects. For photons, no such deviations have been detected. Another line of inquiry involves searching for a tiny but non-zero photon mass. If the photon had even an extremely small mass, it could signal new physics beyond the standard model. Experiments have placed incredibly stringent limits on photon mass. So far, all results are consistent with exactly zero rest mass. If the photon had substructure, it might also possess additional internal degrees of freedom beyond the two polarization states allowed for a massless spin 1 particle. No such extra degrees of freedom have been observed, so within the best tested framework of modern physics, there is nothing inside a photon in the sense of smaller constituent particles. However, the question of inside can also be interpreted differently. Rather than asking about subparticles, we might ask whether the photon contains any internal complexity in its quantum state. For example, a photon can be entangled with another particle. Two photons can be created in an entangled state, such that their polarizations are correlated, even when separated by large distances. This entanglement is not internal structure, but it does show that the quantum state of a photon can encode complex correlations. Similarly, photons can carry orbital angular momentum in addition to their intrinsic spin. In specially structured light beams, the electromagnetic field can have helical phase patterns. Individual photons in such beams carry quantized orbital angular momentum. This does not imply internal composition, but it shows that photons can occupy sophisticated quantum states. These features remind us that elementary does not mean simple in every respect. A photon can participate in intricate quantum phenomena, even if it has no smaller parts. The deeper question remains open in principle. If there is a more fundamental theory underlying the standard model, perhaps involving strings, loops, or other structures, then photons might emerge from that deeper level. But until experimental evidence points in that direction, the photon remains fundamental in our current understanding. Looking deeper requires either higher energies or new kinds of observations. At present, all data are consistent with the photon being a point-like excitation of the electromagnetic field, with no detectable internal structure. So when we ask whether we can look inside a photon, the answer is that we have looked as deeply as current technology allows. What we see is consistent with a fundamental entity, and if photons are not built from smaller parts, that shifts the focus of inquiry. Instead of asking what lies inside them, we begin asking how they arise from the structure of the electromagnetic field itself, and whether that field might be part of an even larger unified framework of forces and particles. Up to this point, we have talked about photons as particles, as quanta, as packets of energy, and as entities with specific properties such as spin and momentum. But all of those descriptions rest on something deeper. In modern physics, photons do not exist in isolation as tiny objects floating through empty space. They arise from something more fundamental, quantum fields. To understand where photons really come from, we have to let go of the idea that particles are the primary building blocks of reality. In classical physics, the world is made of particles moving through space and interacting via forces. Fields were introduced later as convenient tools to describe how forces operate at distance. In quantum field theory, that picture is reversed. Fields are fundamental, particles are excitations of those fields. The electromagnetic field is not something that appears only when light is present. It exists everywhere, even in what we call empty space. Every point in space has associated field values. When nothing observable is happening, the field is in its lowest energy state, known as the vacuum state. A photon appears when the electromagnetic field is excited. That excitation is quantized. The smallest possible excitation corresponds to one photon. This idea can be illustrated by analogy, although no analogy is perfect. Imagine a stretched string. Even when it is still, the string exists and has tension. If you pluck it, a vibration travels along it. That vibration is not a separate object made of smaller pieces. It is a pattern of motion in the string. Now extend that idea beyond physical strings to fields that fill all of space. The electromagnetic field is not made of material substance, in the way a string is made of molecules. But mathematically it behaves like a collection of harmonic oscillators, one at each possible frequency and direction. When these oscillators are quantized, their energy levels become discrete. The ground state corresponds to 0 photons, the first excited state corresponds to 1 photon. Each additional excitation adds another photon to that particular mode. This quantization process is not an arbitrary assumption. It follows from applying the principles of quantum mechanics to classical field equations. Maxwell's equations describe how electric and magnetic fields evolve in space and time. When those equations are promoted to quantum operators and combined with the commutation relations required by quantum mechanics, the result is quantum electrodynamics, or QED. In QED, the electromagnetic field is described by operators that create and annihilate photons. These operators act on quantum states. When a creation operator is applied to the vacuum state, it produces a one-photon state. This language may sound abstract, but it has measurable consequences. The discrete energy levels of the field explain why photons are absorbed and emitted in quantized amounts. The field structure explains interference patterns and wave-like behavior. The operator formalism explains how photons are exchanged between charged particles during interactions. An important aspect of quantum fields is that they are relativistic by construction. The theory respects the principles of special relativity. This ensures that photons, as massless excitations, always travel at the speed of light in vacuum. The fact that the photon is massless is not an independent accident. It is tied to the symmetry of the electromagnetic field. Specifically, the electromagnetic field has a gauge symmetry. This symmetry allows certain transformations of the field without changing observable physics. Gauge symmetry is not just a mathematical convenience, it is a structural principle that determines the form of the interactions. In quantum electrodynamics, requiring local gauge invariance leads directly to the existence of a massless spin-1 particle. That particle is the photon, so photons come from the requirement that the theory describing charged particles must be invariant under certain transformations. The electromagnetic field is introduced to preserve that invariance. Quantizing the field produces photons. In this sense, photons are not added artificially to the theory. They are unavoidable consequences of symmetry principles. Another feature of quantum fields is that they allow for particle creation and destruction. In classical mechanics, particles are conserved objects that persist over time. In quantum field theory, particles can appear and disappear as long as conservation laws are respected. For example, when an excited atom emits light, the atom transitions to a lower energy state, and a photon is created. The electromagnetic field gains one quantum of excitation. Conversely, when a photon is absorbed, the field loses one excitation. This dynamic creation and annihilation is built into the mathematical structure of the theory. It is not something that needs to be inserted manually. The vacuum itself is not empty in the classical sense. Even in its lowest energy state, the electromagnetic field exhibits fluctuations. These vacuum fluctuations can produce measurable effects, such as the Casimir effect, where two closely spaced metal plates experience an attractive force due to changes in vacuum energy between them. These phenomena reinforce the idea that fields, not particles, are fundamental. Photons are temporary excitations of something that always exists. It is also important to clarify what we mean by mode of the field. A mode corresponds to a particular frequency and spatial configuration. The electromagnetic field can be decomposed into many such modes. Each mode behaves like an independent quantum harmonic oscillator. The number of photons in a given mode can be 0, 1, 2, and so on. In a laser, a particular mode contains an enormous number of photons producing a coherent beam. In a single photon experiment, one specific mode is excited by exactly one quantum. The concept of fields extends beyond electromagnetism. The Standard Model describes other forces and particles as excitations of their own fields. The electron is an excitation of the electron field. Quarks are excitations of quark fields. The Higgs boson is an excitation of the Higgs field. What distinguishes the photon is that it is associated with an unbroken gauge symmetry. Because of this symmetry, the photon has zero mass and long-range interactions. When we say that photons come from the electromagnetic field, We are saying that their existence is inseparable from that field structure. There is no photon separate from the field. The photon is the field in a specific excited state. This perspective answers the question of composition in a different way. A photon is not made of smaller building blocks. It is not assembled from sub-particles. It is the smallest possible excitation of a fundamental field. If there were a deeper level beneath quantum fields, if space-time itself were quantized, or if all fields emerged from more basic objects, then photons might ultimately be expressions of that deeper layer. But within our current best-tested framework, fields are fundamental, and photons are their quanta. The field viewpoint also resolves the wave-particle tension discussed earlier. The wave aspect arises from the field equations governing how excitations propagate. The particle aspect arises from the quantized energy levels of the field. When a photon travels through space, what is happening is the evolution of a quantum state of the electromagnetic field. The state spreads and evolves according to relativistic wave equations. When an interaction occurs, the field exchanges one quantum of energy. There is no tiny object flying through space in the classical sense. There is a quantum excitation evolving in a field that permeates all of space-time. Understanding this shift, from particles as fundamental to fields as fundamental, is crucial. It reframes the original question. Instead of asking what a photon is made of, we ask what kind of field gives rise to it and what symmetries define that field. And once we take fields seriously as the foundation of reality in modern physics, it becomes natural to ask whether the electromagnetic field itself might be part of an even larger unified structure, and whether photons are connected to other force carriers in ways that reveal deeper relationships within the standard model. By the time we reach this point, the answer within established physics seems clear. In the standard model, the photon is an elementary particle. It is the massless spin 1 quantum of the electromagnetic field. It has no known internal structure. All high-precision experiments are consistent with it being point-like and indivisible. But physics does not stop at the boundaries of its current model. The standard model itself is known to be incomplete. It does not include gravity in a quantum framework. It does not explain dark matter. It does not fully account for certain asymmetries observed in the universe. So it is reasonable to ask whether photons might be made of something more fundamental in a deeper theory that extends beyond what we currently know. To approach that question responsibly, we need to distinguish between two different possibilities. The first possibility is that photons are composite particles in the same way protons are composite. In that scenario, photons would be built from smaller constituent particles bound together by some interaction. If that were true, we would expect measurable deviations from the predictions of quantum electrodynamics at high energies. Composite particles typically exhibit form factors, internal resonances, or scattering behaviors that reveal substructure. Extensive experiments have looked for such effects. So far, none have been found. Photon interactions at the highest energies accessible to modern accelerators match theoretical predictions for point-like particles with no internal components. If photons were composite at accessible scales, we would almost certainly have detected anomalies by now. The second possibility is more subtle. Photons might not be composite in the traditional sense, but they could emerge from a deeper layer of reality in which the fundamental entities are not particles at all. One of the most widely discussed speculative frameworks in this direction is string theory. In string theory, the fundamental objects are not point particles, but one-dimensional strings vibrating at extremely small scales. Different vibrational modes correspond to different particles. In that framework, what we call a photon would correspond to a particular vibration pattern of a fundamental string. If string theory were correct, photons would not be built from smaller particles in the way atoms are built from protons and electrons. Instead, they would be manifestations of a deeper object, the string itself. The structure of the photon would then be encoded in the properties of that vibrational mode. However, string theory remains unverified experimentally. The energy scales at which string effects would become apparent are thought to be near the Planck scale, around 10 to the power of 19 giga-electron-volts. That is far beyond the reach of current or foreseeable particle accelerators. Without experimental evidence, string theory remains a mathematical framework rather than an established description of nature. Another line of speculation involves quantum gravity. If space-time itself has a discrete or quantized structure at extremely small scales, then the electromagnetic field, and therefore photons, might emerge from that deeper geometry. Some approaches, such as loop quantum gravity, attempt to describe space-time as built from fundamental discrete elements. In such theories, photons might not be made of smaller particles, but could be emergent excitations of a more fundamental space-time structure. Again, this is speculative. There is no direct experimental evidence yet that space-time is discrete at the Planck scale, nor that photons reveal such discreteness. There is also the possibility that the standard model gauge symmetries themselves emerge from a deeper unified theory. In grand unified theories, the electromagnetic force is combined with the weak and strong nuclear forces at extremely high energies. In such models, the photon is related to other gauge bosons through symmetry-breaking processes that occurred in the early universe. In the electroweak theory, which is experimentally confirmed, the photon is already understood as a mixture of two more fundamental gauge fields associated with a larger symmetry group. Before symmetry breaking in the early universe, the electromagnetic and weak forces were unified. The photon and the Z-boson arise from combinations of underlying fields. This does not mean that the photon is composite in a mechanical sense, but it does show that its identity is tied to deeper symmetries. At very high energies, what we call the photon today did not exist as a distinct entity. It emerged when the unified electroweak symmetry was broken as the universe cooled. That example illustrates an important point. More fundamental does not always mean smaller pieces inside. It can mean a deeper level of symmetry from which familiar particles emerge. Another question sometimes raised is whether photons might have tiny deviations from exact masslessness. Experiments have placed extraordinarily tight upper limits on photon mass. If photons had even a minute mass, it would change the behavior of electromagnetic fields over large distances. So far, all observations are consistent with zero rest mass, within extremely small experimental uncertainty. If a non-zero mass were discovered, it would indicate physics beyond the standard model. But it would not necessarily imply internal composition. It would imply a modification of gauge symmetry or the introduction of new fields. High-energy astrophysical observations also constrain possible substructure. Photons travelling across billions of light-years from distant galaxies show no signs of energy-dependent speed variations. Some speculative quantum gravity models predict such variations. Current observations place strong limits on those possibilities. All of this leads to a cautious conclusion. Within the experimentally tested framework of quantum field theory, photons are fundamental. They are not made of smaller constituents. No measurable evidence suggests internal structure. Beyond that framework, there are theoretical ideas suggesting deeper layers of reality. But until those ideas produce experimentally testable predictions, and those predictions are confirmed, they remain hypotheses. It is also worth reflecting on how often physics has uncovered deeper structure in the past. Atoms were once thought indivisible. They were later found to contain nuclei and electrons. Nuclei were later found to contain quarks. Each time, experiments revealed discrepancies that pointed toward new layers. For photons, no such discrepancies have appeared. Quantum electrodynamics predicts photon behavior with extraordinary precision. Deviations that would indicate substructure have not been observed. That does not mean photons are absolutely fundamental in an ultimate metaphysical sense. It means that within our current understanding and experimental reach, they behave as fundamental entities. So if we ask whether photons are made of anything more fundamental, the honest answer today is that we do not have evidence that they are. They may emerge from deeper symmetries or structures in speculative theories, but no data currently requires such a conclusion, and this realization shifts the focus again. If photons are fundamental in the best tested theory we have, then the more productive question may not be about smaller pieces inside them, but about how they function as carriers of one of nature's fundamental interactions, and how their properties shape the structure of the universe itself. If we step back from the question of internal structure and look at the broader picture of physics, photons occupy a very specific and powerful role. They are not just quanta of light, they are the carriers of one of the four fundamental forces of nature, the electromagnetic force. To understand what that means, we need to briefly review how modern physics organizes the fundamental interactions. According to the Standard Model, there are four known fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each of these forces is associated with a field. In quantum field theory, forces are mediated by particles that arise as excitations of those fields. These mediating particles are called gauge bosons. The photon is the gauge boson of electromagnetism. This statement carries significant implications. It means that whenever two charged particles interact electrically, the interaction can be described in terms of photon exchange. In classical electromagnetism, we describe forces using electric and magnetic fields. A charged particle creates an electric field. Another charged particle placed in that field experiences a force. The field appears continuous and smooth. In quantum electrodynamics, that smooth field description is replaced with a more detailed picture. The electromagnetic interaction arises from the exchange of virtual photons between charged particles. Virtual photons are not directly observable in the same way as real photons, such as those detected by a camera. They are internal components of the mathematical description of interactions. In Feynman diagrams, graphical tools used to calculate interaction probabilities, charged particles are shown emitting and absorbing virtual photons. These exchanges account for the electromagnetic force. For example, consider two electrons repelling each other. In the quantum description, one electron emits a virtual photon, which is absorbed by the other electron. This exchange transfers momentum and energy in a way that reproduces the classical Coulomb force when averaged over many interactions. The electromagnetic force has infinite range. This is directly related to the photon's masslessness. In quantum field theory, the range of a force depends on the mass of its mediator. A massless mediator produces a long-range force that decreases with distance but never drops abruptly to zero. By contrast, the weak nuclear force is mediated by the W and Z bosons, which are very massive. As a result, the weak force has a very short range, effective only at subatomic distances. The strong nuclear force, which binds quarks together inside protons and neutrons, is mediated by gluons. Gluons are also massless in theory, but because of the way the strong force behaves, due to a property called confinement, the force does not extend freely over long distances in the same way electromagnetism does. Gravity in classical theory is described by general relativity as the curvature of space-time. In hypothetical quantum gravity theories, the mediator of gravity would be the graviton, a massless spin-2 particle. However, gravitons have not been experimentally detected. Within this framework, the photon stands out as the mediator of the only long-range force described by a fully established quantum field theory with extraordinary precision. The photon's properties are precisely what make electromagnetism behave the way it does. Because the photon has spin 1, electromagnetic interactions have specific symmetry properties. Because it is massless, the force has infinite range. Because it is electrically neutral, photons do not directly couple to themselves in ordinary quantum electrodynamics. That last point is important. Photons do not normally interact with other photons. In classical electromagnetism, light waves pass through each other without disturbance. In quantum electrodynamics, photon-photon scattering is technically possible, but occurs only through higher order processes involving virtual charge particles, and the probability is extremely small. This is a consequence of the structure of the electromagnetic field and its gauge symmetry. The U1 gauge symmetry underlying electromagnetism is abelian, meaning that the field does not carry charge itself. This differs from the strong nuclear force, where gluons carry colour charge and interact with one another directly. The electroweak theory provides further insight into the photon's place among the forces. At high energies, electromagnetism and the weak force are unified into a single electroweak interaction. In that regime, there are 4 gauge fields associated with a larger symmetry group. As the universe cooled after the Big Bang, spontaneous symmetry breaking occurred through the Higgs mechanism. This symmetry breaking produced the photon and the Z boson as mixtures of the original gauge fields. The photon remained massless. The Z boson acquired mass. The W bosons also acquired mass. This means that the photon we observe today is not simply an isolated entity. It is the result of symmetry breaking in the early universe. At extremely high energies, the distinction between electromagnetic and weak interactions disappears. In that sense, the photon is part of a broader structure of forces. It is one component of the electro-weak interaction. The role of photons in nature is pervasive. Electromagnetism governs atomic structure. The attraction between electrons and atomic nuclei is electromagnetic. Chemical bonds are electromagnetic. The rigidity of solid matter arises from electromagnetic interactions between atoms. Light itself is electromagnetic radiation. Vision, photosynthesis, radio communication, X-rays in medicine, all involve photons. On a cosmic scale, photons fill the universe. The cosmic microwave background radiation consists of photons left over from the early universe, now cooled to a temperature of about 2.7 Kelvin. These photons provide a snapshot of the universe approximately 380,000 years after the Big Bang. Photons also carry information across vast distances. When we observe distant galaxies, the photons reaching our telescopes have travelled for millions or billions of years. Their frequencies may be redshifted due to cosmic expansion, but their fundamental properties remain unchanged. The interaction between photons and gravity is also significant. Although photons have no rest mass, they are affected by gravity because gravity couples to energy and momentum, not just mass. Light bends around massive objects, a phenomenon known as gravitational lensing. This effect was one of the early confirmations of general relativity. Photons do not carry electric charge, but they carry energy and momentum, and therefore they respond to space-time curvature. In particle physics experiments, photons are both tools and subjects of study. High-energy photons can probe internal structure of matter. They can produce particle-antiparticle pairs when interacting with nuclei. They can be used to test fundamental symmetries. Despite all of these roles, photons remain simple in one crucial respect. They have no known internal components. Their participation in forces does not arise from internal mechanisms, but from their identity as gauge bosons of a fundamental symmetry. So when we ask what photons are made of, and whether they have smaller pieces inside, it is worth remembering that their importance does not depend on internal complexity. It depends on their role in the structure of interactions. They are not built from smaller building blocks within the standard model, they are building blocks of interactions themselves. And that brings us to another layer of inquiry. If photons mediate the electromagnetic force and travel through space as excitations of a field, what exactly happens to them during that journey, especially when they move through different environments or extreme gravitational conditions? When we imagine something travelling, we usually picture an object moving along a path through space. A ball follows a trajectory. A car moves from one point to another. It has a position at each moment in time. It occupies space as it goes. Photons do not travel in that classical sense. In everyday language, we say that light travels from the sun to Earth in about 8 minutes. We say that a photon leaves a distant galaxy and crosses billions of light years before reaching a telescope. These statements are useful, but they hide a deeper question. What is actually happening during that journey? To answer that, we need to return to the quantum field description. A photon is an excitation of the electromagnetic field. When it is created, say when an atom transitions from a higher energy state to a lower one, the electromagnetic field enters a new quantum state, containing one excitation in a particular mode. That excitation evolves according to the equations governing the field. In classical electromagnetism, an electromagnetic wave propagates through space as oscillating electric and magnetic fields. The wave spreads out, diffracts, and interferes according to Maxwell's equations. In quantum theory, the probability amplitude associated with the photon evolves in a way consistent with those same equations. The wave aspect of the photon is expressed through this evolving amplitude. What does that mean in practical terms? It means that between emission and detection, the photon is described not as a tiny particle following a precise trajectory, but as a quantum state spreading through space. If a photon is emitted in a specific direction with a narrow range of frequencies, its wave packet will move outward at the speed of light. The centre of that packet will advance at c, but the packet itself can spread over time, depending on how it was prepared. If the photon passes through an environment such as a lens or a slit, the wave function changes according to the boundary conditions imposed by those objects. The probability distribution adjusts, producing patterns such as focusing or interference. This is not a metaphorical statement. The mathematics of quantum field theory predicts how the amplitude evolves in space and time. The results match observed phenomena. Importantly, there is no need to imagine a solid object moving through a medium. The electromagnetic field itself evolves, and the excitation corresponding to one photon is part of that evolution. Another key point is that photons do not gradually lose energy while travelling through empty space. In a perfect vacuum, a photon of a given frequency retains that frequency indefinitely, unless it interacts with something. This conservation of energy during free propagation is a consequence of the time translation symmetry of space-time. In other words, because the laws of physics do not change over time in a uniform way, energy is conserved. However, when photons travel through an expanding universe, their frequency can change. This is known as cosmological redshift. As space itself expands, the wavelength of travelling photons stretches, their frequency decreases, and therefore their energy decreases. This effect is not caused by friction or by interaction with matter. It arises from the dynamic geometry of space-time described by general relativity. The photon's energy changes because the background space-time through which it travels is evolving. Similarly, when photons move in a gravitational field, their frequency can shift. If a photon climbs out of a gravitational well, its frequency decreases. This is gravitational redshift. Conversely, if it falls into a gravitational well, its frequency increases. These shifts are consequences of the relationship between energy and space-time curvature. Photons do not have rest mass, but they carry energy and momentum, and gravity couples to energy momentum. From the standpoint of relativity, photons follow paths called null geodesics. These are trajectories through space-time along which the space-time interval is zero. This formal statement captures the fact that photons always move at the speed of light in vacuum. One subtle but often misunderstood idea is that from the perspective of relativity, no proper time elapses along a photon's path. The mathematical interval between emission and absorption along a light-like path is zero. This does not mean that photons experience no time in a subjective sense. Photons do not have frames of reference in the same way massive observers do. It means that within the geometry of space-time, the proper time along a light-like trajectory is zero. When a photon interacts with matter, its journey ends in a discrete event. The electromagnetic field loses one quantum of excitation. The energy and momentum carried by the photon are transferred to the absorbing system. For example, in the photoelectric effect, a photon strikes a metal surface and transfers its energy to an electron. The photon ceases to exist as a photon. Its energy becomes kinetic energy of the electron and contributes to overcoming the electron's binding energy. In other cases, photons may scatter elastically or inelastically. In elastic scattering, such as Thomson scattering at low energies, the photon changes direction but retains its energy. In inelastic scattering, such as Compton scattering, the photon transfers part of its energy to an electron and emerges with reduced frequency. Throughout its travel, the photon's behavior is governed by the structure of the electromagnetic field and the geometry of space-time. Another interesting aspect of photon travel is coherence. In a laser beam, photons are emitted in a coherent state. Their phases are correlated. As they propagate, that coherence can be maintained over long distances if the medium does not disrupt it. In contrast, thermal light from a light bulb consists of photons emitted independently by many atoms. Their phases are uncorrelated. As a result, the light does not produce stable interference patterns unless filtered carefully. From the quantum perspective, these differences are encoded in the structure of the field's quantum state. It is also worth noting that photons can travel through matter at speeds lower than c. When light enters a medium such as glass or water, its effective speed decreases. This does not mean that individual photons slow down in the simple sense of moving more slowly through empty space. Instead, the interaction between the electromagnetic field and the charged particles in the medium alters the propagation of the wave packet. In a medium, photons are repeatedly absorbed and re-emitted or interact with collective excitations of the material. The overall effect is that the group velocity of the wave is reduced. But between interactions, the fundamental propagation in vacuum still occurs at c. So what happens to a photon when it travels? It propagates as an evolving excitation of the electromagnetic field, described by a quantum state that spreads and changes according to relativistic wave equations. It carries energy and momentum determined by its frequency. It follows the structure of space-time, responding to curvature and expansion. It interacts discretely with matter when the opportunity arises. At no point during its journey does it reveal internal components or substructure. Its behavior remains consistent with being a fundamental quantum of a field. And when that journey brings it near extreme environments, such as regions of intense gravitational curvature around compact objects, the interplay between photon propagation and space-time geometry becomes even more pronounced, leading us naturally to consider what happens when light approaches one of the most extreme objects known in physics. When we talk about photons travelling through space, most of the time we imagine relatively calm conditions. Interstellar space, planetary systems, laboratory experiments. But there are regions of the universe where space-time itself is so strongly curved that the behaviour of light becomes dramatically different. Nowhere is this more evident than near a black hole. A black hole is not a solid object in the conventional sense. It is a region of space-time where gravity is so strong that nothing, not even light, can escape once it crosses a boundary known as the event horizon. That boundary is not a physical surface, it is a mathematical surface defined by the geometry of space-time. To understand what happens to light near a black hole, we need to combine what we know about photons with what general relativity tells us about gravity. General relativity describes gravity not as a force, but as the curvature of space-time caused by mass and energy. Massive objects warp the geometry around them. Objects moving through that curved geometry follow paths determined by it. Photons, despite having no rest mass, still follow these curved paths. Their motion is governed by the structure of space-time. They travel along null geodesics, which are the paths allowed for light in curved space-time. Far from a black hole, the curvature is weak, and the bending of light is small. This bending is known as gravitational lensing. Light from distant stars can curve around massive galaxies, producing multiple images or arcs. These effects have been observed and measured with high precision. As photons move closer to a black hole, the curvature becomes extreme. Light passing near the black hole can be deflected by large angles. There exists a region called the photon sphere, where gravity is strong enough that photons can orbit the black hole in unstable circular paths. The photon sphere lies outside the event horizon. At that radius, a photon moving tangentially can circle the black hole. However, the orbit is unstable. A small perturbation will cause the photon either to spiral outward or fall inward. This fact alone tells us something important. The photon does not resist gravity because it has no mass. Its energy and momentum are sufficient for gravity to affect it. As a photon approaches the event horizon, several effects become significant. One is gravitational redshift. If a photon is emitted from near a black hole and travels outward to a distant observer, its frequency decreases. The stronger the gravitational field at the point of emission, the more pronounced the redshift. From the perspective of a distant observer, a photon emitted just outside the event horizon appears increasingly redshifted as its point of origin approaches the horizon. In the limit, as the emission point approaches the horizon, the photon's frequency appears to drop towards zero. This does not mean the photon loses energy in a mechanical sense. It means that the measurement of its energy depends on the gravitational potential difference between emission and observation. Another effect is time dilation. From the viewpoint of a distant observer, processes near the event horizon appear to slow down. A photon emitted closer and closer to the horizon appears to take longer and longer to reach the observer. In fact, in the coordinate time of the distant observer, a photon emitted exactly at the horizon would never arrive. However, from the local perspective near the black hole, nothing unusual happens at the horizon itself. The photon continues moving at the speed of light locally. The strange behavior arises from how time and space are related between different observers in curved space-time. Now consider a photon falling toward a black hole. As it moves inward, its frequency increases from the perspective of an observer deeper in the gravitational field. This is gravitational blue shift. The photon's energy appears higher to that observer. Once the photon crosses the event horizon, it cannot escape. Inside the horizon, all future directed paths lead toward the singularity at the center. The geometry of space-time is such that moving outward becomes as impossible as moving backward in time. It is important to clarify what this means. The photon does not encounter a wall or a physical barrier at the horizon. It simply finds that the structure of space-time no longer permits trajectories that lead outward. The question then arises, what happens to the photon after crossing the horizon? According to classical general relativity, it continues toward the singularity. The singularity is a region where space-time curvature becomes infinite, and the classical equations break down. At that point, our current understanding is incomplete. Quantum gravity would likely be required to describe what truly happens. This brings us to an intersection between quantum field theory and curved space-time. In the 1970s, Stephen Hawking showed that black holes are not entirely black. Quantum effects near the event horizon can produce radiation now known as Hawking radiation. This radiation arises from quantum fluctuations of fields near the horizon. The process is often described in simplified terms as particle-antiparticle pairs forming near the horizon, with one falling in and the other escaping. The escaping particle appears as radiation emitted by the black hole. For photons specifically, the electromagnetic field can participate in these quantum processes. The result is that black holes emit radiation with a thermal spectrum. This radiation includes photons. Hawking radiation is extremely weak for astrophysical black holes. For a black hole with the mass of the Sun, the temperature is far below the cosmic microwave background temperature. But in principle, black holes emit photons due to quantum field effects in curved space-time. This suggests something deeper. The behavior of photons near a black hole is not just about trajectories. It involves the interplay between quantum fields and space-time geometry. In curved space-time, the concept of a particle can become observer-dependent. What one observer calls vacuum, another may interpret as containing particles. The definition of a photon can depend on the choice of reference frame. This subtlety shows that photons are not little objects travelling independently of the background. They're excitations of a field embedded in space-time. When space-time curvature becomes extreme, the definition of those excitations becomes more complicated. Another interesting phenomenon occurs in strong gravitational lensing. Photons can loop around a black hole multiple times before escaping. This produces a series of increasingly faint images of background objects. The Event Horizon Telescope's image of the black hole in M87 shows a bright ring of light corresponding to photons that have orbited near the photon sphere before escaping toward Earth. These observations confirm the predictions of general relativity and the behavior of light in extreme curvature. Throughout all of this, the photon retains its fundamental properties. It remains massless, it travels locally at sea, it carries energy and momentum determined by its frequency. What changes is not the photon's internal structure, but the geometry through which it moves. Near a black hole, spacetime itself becomes dynamic and highly curved. The photon's path bends accordingly. Its frequency shifts depending on gravitational potential. Its apparent timing changes depending on the observer. The photon does not reveal hidden substructure under these conditions. It continues to behave as a fundamental excitation of the electromagnetic field. But the extreme environment highlights something important. Photons cannot be understood independently of space-time. Their behavior is inseparable from the geometry of the universe, and when we push further toward the deepest questions about singularities, quantum gravity, and the ultimate structure of space-time, we begin to approach a point where even the familiar concepts of fields and particles may need to be revised. When we talk about particles in physics, one of the most common processes we study is decay. Many particles are unstable. They transform into other particles after a certain amount of time. A neutron outside a nucleus will eventually decay into a proton, an electron, and a neutrino. Heavy quarks decay into lighter ones. Even some force-carrying particles like the W and Z bosons decay almost immediately after being produced. So it is natural to ask whether the photon could ever decay or break apart. At first glance, this seems unlikely. Photons are massless, they are stable. We observe light from distant galaxies that has travelled for billions of years without disappearing. That fact alone suggests extraordinary stability. But physics does not rely on intuition alone. To answer the question properly, we need to look at conservation laws and the structure of the Standard Model. In quantum field theory, whether a particle can decay depends on several conditions. The most important are conservation of energy, conservation of momentum, conservation of charge, and conservation of other quantum numbers such as angular momentum. For a particle to decay, there must exist a combination of lighter particles whose total energy and momentum can match that of the original particle. Now consider a photon in empty space. It has energy E and momentum P, related by E equals pc, because it is massless. If it were to decay into two particles, those particles would have to conserve total energy and total momentum. Suppose we imagine a photon decaying into two photons. That would not change anything meaningful. It would just be a redescription of the same electromagnetic excitation, and in fact, such a spontaneous splitting does not occur in ordinary vacuum. Quantum electrodynamics forbids it at lowest order because of the linear nature of Maxwell's equations and the structure of the interaction terms. What about decaying into an electron and a positron? That process is known as pair production, but it cannot occur for a single photon in empty space. The reason is conservation of momentum. If a photon in vacuum tried to produce an electron-positron pair, there would be no way to simultaneously conserve both energy and momentum unless another object participates in the interaction. In practice, pair production occurs when a high-energy photon passes near a nucleus. The nucleus absorbs some momentum, making conservation laws possible. Without that third body, a lone photon cannot decay into massive particles in vacuum. This already tells us something important. In empty space, A photon cannot spontaneously decay into other particles if energy and momentum conservation cannot be satisfied. Could it decay into massless particles? In the Standard Model, there are very few massless particles. The photon itself is massless. The gluon is massless, but gluons carry color charge and do not propagate freely outside hadrons due to confinement. Neutrinos have extremely small but non-zero mass, so there are no lighter neutral particles available for a photon to decay into while conserving all required quantities. Additionally, the photon carries spin equal to 1. Any decay products would need to combine in a way that conserves angular momentum. The available options are tightly constrained. The Standard Model predicts that the photon is exactly stable. There is no allowed decay channel consistent with known conservation laws and particle content. Experimental evidence strongly supports this. We observe photons travelling across cosmic distances from sources billions of light years away. If photons had even a tiny probability of spontaneous decay, high-energy photons from distant astrophysical events would disappear or transform before reaching us. No such effect has been observed. In fact, astrophysical observations place extremely stringent lower bounds on photon lifetime. If photons decay at all, their lifetime must be vastly longer than the age of the universe. That addresses spontaneous decay in vacuum. But what about breaking apart under extreme conditions? In strong electromagnetic fields, quantum electrodynamics predicts nonlinear effects. For example, photon-photon scattering can occur through higher-order processes involving virtual charged particles. In such processes, two photons interact indirectly through loops of virtual electrons and positrons. However, these interactions do not cause photons to fragment into smaller pieces. They represent scattering events that conserve photon identity as quanta of the electromagnetic field. In certain high-energy astrophysical environments, such as near neutron stars with extremely strong magnetic fields, quantum electrodynamics predicts phenomena like photon splitting. In photon splitting, one high-energy photon can split into two lower-energy photons in the presence of a strong magnetic field. Even in this case, the process does not reveal internal components. It is a higher-order interaction mediated by the electromagnetic field and influenced by external conditions. The photon does not break into smaller subparticles. Instead, energy is redistributed into two new photon excitations consistent with conservation laws. This distinction is crucial. When a composite particle breaks apart, such as a proton splitting into quarks in a high-energy collision, the constituents are revealed. When a photon participates in a splitting process, the products are still photons, not smaller entities inside it. Another possible transformation involves interactions with gravity. Could a photon decay due to gravitational effects? General relativity does not predict spontaneous photon decay. Photons follow geodesics in curved space-time. They may be redshifted or blueshifted, but they do not disintegrate. Some speculative theories beyond the Standard Model have explored the possibility that photons might have a tiny mass, or might mix with hypothetical particles such as axions. In certain models, photons could oscillate into axion-like particles in the presence of strong magnetic fields. These are active areas of experimental research. However, no confirmed evidence for photon decay or mixing into unknown particles has been found. Observations of light from distant astronomical sources strongly constrain such possibilities. The stability of the photon is deeply connected to gauge symmetry. In quantum electrodynamics, gauge invariance protects the masslessness and stability of the photon. As long as that symmetry holds, the photon remains exactly massless and does not decay. If a future theory were to break that symmetry slightly, new phenomena could arise, but such a theory would need to match the extremely precise experimental data currently available. So within the established framework of modern physics, the photon cannot decay spontaneously in empty space. It cannot break apart into smaller constituents because it has no known constituents. It can transform in interactions, converting its energy into matter under appropriate conditions. It can be absorbed or scattered. It can split into other photons in extreme environments, but it does not fragment into subphotons. This reinforces the earlier conclusion. The photon is fundamental in the Standard Model. Its stability is not accidental, but rooted in the symmetries that define electromagnetism. And with that in mind, the remaining question is not whether the photon can break apart, but what all of these properties together, masslessness, quantized energy, field origin, stability, tell us about the nature of light itself and how it fits into our broader understanding of reality. We began with a simple question. What is a photon really made of? At first, it seemed like the kind of question that should have a familiar answer. Most things we encounter are made of smaller things. Molecules are made of atoms. Atoms are made of protons, neutrons, and electrons. Protons and neutrons are made of quarks. Each time physics has looked deeper, it has uncovered another layer. But when we followed that pattern toward the photon, the pattern stopped. We found that light does not reveal internal components under the most precise experiments ever performed. High-energy scattering experiments show no sign of substructure. Quantum electrodynamics predicts photon behavior with extraordinary accuracy, and observations match those predictions to many decimal places. The photon, in the Standard Model, is elementary. That does not mean it is simple in a naive sense. It means it is not built from smaller constituent particles within the framework of the theory. We saw that the photon is the quantum of the electromagnetic field. The field itself exists everywhere in space. When it is excited in discrete units, those excitations are photons. There is no tiny solid core inside them. There are no smaller mechanical pieces hidden beneath the surface. Instead, their properties arise from symmetry. The photon has zero rest mass because the electromagnetic field possesses gauge symmetry that forbids a mass term. It has spin equal to 1 because of how it transforms under rotations in space-time. It has two polarization states because of the constraints imposed by being massless and relativistic. Its energy is determined by frequency through E equals h nu. That relationship is not arbitrary. It is built into the quantization of the field. The photon represents the smallest possible packet of electromagnetic energy at a given frequency. We examined whether photons behave like particles or waves. The answer was that they do not fit cleanly into either classical category. They propagate according to wave equations. They interact in discrete localized events. The wave-like behavior describes how probability amplitudes evolve. The particle-like behavior describes how energy is transferred. We looked at whether photons have size or shape. In classical terms, they do not. Their spatial extent depends on how their quantum state is prepared. A photon can be described by a wave packet that spans large distances, or by a more localized distribution, but there is no rigid geometric boundary. We asked whether there is anything inside a photon. All available evidence says no. No internal components have been detected. No deviations from point-like behavior have been observed at accessible energies. We considered speculative theories, string theory, quantum gravity, grand unification. These frameworks suggest that photons might emerge from deeper structures or symmetries, but until experimental confirmation appears, the photon remains fundamental in the best-tested description of nature. We examined how photons mediate the electromagnetic force. They are not just carriers of light, they are the mechanism by which charged particles interact. Every electric force, every magnetic field, every chemical bond ultimately traces back to the exchange of photons. We followed photons to the edge of black holes. We saw that their paths bend in curved space-time. Their frequencies shift in gravitational fields. They follow the geometry of the universe itself. Even there, under extreme conditions, they behave consistently with being massless excitations of a field. We ask whether a photon could decay or break apart. The answer, within the Standard Model, is that it cannot spontaneously decay in empty space. Conservation laws and gauge symmetry protect its stability. It can transform its energy into matter under the right conditions, but it does not fragment into smaller building blocks. So what have we learned? We have learned that the question, what is a photon made of, may not have the kind of answer we expect from everyday experience. The photon is not made of smaller pieces in the same way that matter is. It is not assembled from subcomponents. Instead, it is a fundamental excitation of a field that permeates all of space-time. This shifts the meaning of composition. At deeper levels of physics, the language of made of gives way to the language of emerges from and is defined by. The photon is defined by the structure of the electromagnetic field and by the symmetries of space-time. It has energy tied to frequency. It has momentum tied to energy. It has spin and polarization determined by transformation properties. It travels at the speed of light because it is massless. It mediates the electromagnetic force because gauge symmetry requires it. In other words, the photon is not built from smaller bricks. It is one of the bricks. And yet, even that metaphor has limits. In quantum field theory, fields are more fundamental than particles. Photons are excitations of something deeper than objects in space. They are patterns in a field that exists everywhere. The deeper we look, the less the universe resembles a collection of tiny solid things, and the more it resembles a network of interacting fields governed by symmetry and geometry. Light, which seems so ordinary, turns out to be one of the clearest windows into that structure. Every time you switch on a lamp, every time sunlight reaches your eyes, every time a radio signal crosses a city, countless photons are being created and absorbed. Each one is a precise quantum of the electromagnetic field, carrying energy in discrete units, obeying conservation laws shaped by the geometry of space-time. We began with the idea that perhaps, like atoms or protons, photons might conceal a smaller internal world. Instead, we arrived at something different, a recognition that some aspects of nature appear, at least for now, to be fundamental. Whether future theories will reveal a deeper layer remains an open question. Physics has surprised us before. But as far as our current knowledge extends, the photon stands as a basic unit of reality, massless, stable, quantized, and inseparable from the field that gives rise to it. And when we look at light again, whether from a distant star or the screen in front of us, we are not seeing tiny object flying through space in the classical sense. We are witnessing the behavior of one of the universe's most fundamental quantum excitations, quietly connecting matter, energy, space, and time.